Good morning, everybody. Can you guys hear and or see me? Hopefully both, as always. Wait till I get a thumbs up, maybe a thumbs down. Oh, no one in chat? All right. Okay, good. Thank you, Sabrina. I appreciate it. Otherwise, we'd be spending 10 minutes wondering if you guys can see me. Alrighty, let's take a peek at our E-class here and see what the schedule is looking like. So today we're at lecture 9 already. Can you guys believe it? And this is a good one. This is one of the most requested lectures I get, especially before the class starts. As we know, it's a Civi class, but we have a lot of nice, wonderful students from Mechie, some from materials, some from chemical. It's actually quite a nice distribution of students. And when they're approaching me to ask if they can take the course, one of the things I always got was, well, will you cover contact? So yes, today we'll be covering contact. So the official title of the lecture here is Constraints and Contact, but as you guys will see, contact is a very specific form of a constraint. So they're going to be very intertied. We're going to cover constraints just to kind of get a feel for what they are. And then we're going to go into contact. Now, contact is really funny because mathematically, it absolutely sucks. You never want to get into the math of contact on, let's say, a final exam because you guys will be sitting there for hours and hours. So the nice part is, as we said, after we covered linear analysis, which was kind of at the end of lecture 6 here, so this cutoff, the rest were mainly just focusing on how to implement it in ABAQUS. We did some theory in the Newton-Raphson method, but as you guys remember last lecture when we did material plasticity or material nonlinearity, we didn't really get into too much detail about the theory and the calculations behind it. And that's going to be the same today. We're going to show you guys kind of what's going on, but we're not going to really focus on, all right, this is the mathematical theory, this is this. We're just going to show you guys what it is, and we're going to spend a lot of time today, as you guys can see, just doing examples in ABAQUS, showing you guys how to use contact and some kind of tips or tricks, if you guys will, to make sure that the analysis goes smoothly. I think I've said it before, but usually contact is the thing that's going to make your model diverge. Material plasticity, it's a little complex, but once you get your head around it, it's very easy to implement. And it's actually not too bad for the solver or the system either. It's when contact comes into play, especially models with a large amount of contact. That's when things get a little bit messy, if you will. So today we're going to be covering contact. After today, so next week, we're going to be covering lecture 10, which will be instability. So we're going to cover things like buckling. We're going to cover things like the arc length method, stuff like that. So that'll be a nice fun lecture. And then after that, we have lecture 11, which is just extra examples. So I'm not sure if I'll hold this in person, but what I'm basically doing was every time a student kind of talked to me on the side there, I figured out what would be good to show in this course. So everything in this extra examples, well, not everything, because example 1 and 2, the linear analysis kind of goes back up here, but things like concrete beams, thermal modeling, those will not be in the exam. Okay, so all these extra topics, that's a better word to describe it, extra topics, they will not be in the final exam. But I thought if you guys are civil engineers, you guys are mechanical engineers or chemical engineers, these are probably good things to know how to do. So I'm going to include them kind of for your benefits. If they help with your project, that's great, but don't expect things like concrete or thermal in the final exam at all. So how does that sound to you guys? Does that sound good so far? Hoping so. Thumbs up, thumbs down. All right, I got it good. Perfect. So that's it for this part right here. Final exam. I had no issues, or no one messaged me at least, with issues concerning the date that we discussed. So if I were to pull up the calendar here, we said that we are going to start the exam. And I'll probably give it out Sunday night. What would you guys prefer, a Sunday night or Monday morning sort of thing? I'm scared if I give it out Sunday nights, you guys will stay up late that Sunday night. And maybe it's nicer if you guys have it Monday. Monday? Okay, so I will send it out Monday morning. So Monday, April 5th. And I currently have it due for Saturday the 10th at 5 p.m. No, at noon. Or which is it? I think it's at noon because it was supposed to be due Friday, but you guys said you prefer Saturday. So Saturday, April 10th, 12 p.m., that's going to be the due date for the final exam. So you guys will have a full 5 days to complete it. I'm hoping you guys think that this is fair, this is enough time. So before we again cement this, is everybody fine with this final exam date? I don't want anybody stressing over it. This should be a nice, fun, happy class. And if you guys are stressing, then it's not a fun, happy class. All right. If you guys do have any concerns, you guys have my email, just let me know. So that's going to be for the final exam. And then we switch the project date to April 23rd. So it was the same date as before, which is a Friday, except we extended it by 1 week. So after you guys submit your final exam, final project, you guys will be done for this course. So I'm hoping this course was good so far for you guys. I hope you guys were able to learn a lot. We still have a lot to cover with contact and instability, but things are wrapping up, guys. So congratulations for making it this far, and let's hopefully finish strong. Hopefully. All right, so we got our assignments. Assignment 8 will be out today, and I'll come back to assignment 8, and once we're done the examples, we'll go over the assignments, because I guarantee if I show you the assignment right now, it's not going to make very much sense. So we're going to do our examples first, and then we're going to go to the assignments, and you guys are going to say, okay, hopefully this isn't too bad. So before we begin, I just want to again emphasize, as we can see from the lecture today, we only have a total of 13 slides, and 3 of them are just these kind of title slides. So not a lot of theory to go over today at all. Again, the focus now is more on how to implement it into ABAQUS. If we were to discuss the theory of contact, as well as things like plasticity, things are going to get really gross. It's going to take probably a whole semester just to go over that. But I'm actually going to ask you guys a question, all, I guess, 14 of you guys, because this is something that I'm curious about. This was something Dr. Sammer was curious about too. If we were to create a course, a whole new Civi course, focusing on just the mathematics of plasticity, as well as things like contact formulations, would that be of interest to you guys, or are you guys thinking that's just a nerd course that no one wants to do? What do you guys think? Would that be of interest to you guys, or would Dr. Sammer and I be wasting our time creating that course? The mathematics of plasticity, as well as contact, things like that. Of interest or not really? You guys are shy today? Daylight savings have you shy? Well, it's actually not really today. You guys have been shy basically most days, but yeah. Yeah, no, exactly. It's an interesting topic, but it would definitely be a dry class. Think of all the mathematics we did here, and just imagine that for 3 straight hours. It's not a lot of fun for sure. But again, it is one of those. You know what? To me, I think it'd be a great audit course. You have the knowledge, but you're not tested. You don't have to do the assignments, anything like that. That's my opinion, but who knows? All right, so we're going to begin. Well, before we begin, actually, I had to do some due diligence. Is there any questions? Are you guys okay so far, or is there anything that's on your guys' mind before we begin today's lecture? We got a lot of examples to go over today, so hopefully it'll be nice and fun. All right, I'm not seeing any questions. If you guys do have any questions, just let me know. I'm still finalizing the questions for the final exam, so next week I promise you guys, before we begin the lecture, I'm going to tell you guys how many questions are going to be on the final, and I'm going to tell you what topics they will be on. Okay, so that'll be kind of my gift to you guys before the final exam. How many questions, as long as the topics of each one of the questions. So if you guys are concerned about that, don't worry. We will do that next lecture together. All right, so let's begin. Again, nice, short theory section, lots of examples. So lecture 9, we're going to be covering 2 things, constraints and contact. And even though they sound like different things, and even though they're separated in ABAQUS, they're going to be essentially the exact same thing. Contact is a specific form of a constraint. So let's start off with constraints. And I put constraints in ABAQUS because, again, we're not going to go into the theory too much. I'm going to show you guys the most simple example of the theory, and that's going to be it. So the question is, well, what exactly is a constraint? Well, constraints are used to define a relationship or an extra condition between the unknown variables. As you guys know, if we have a beam, our unknown variables are typically those nodal displacements. Those are what we're going after. And up until this point, the only real constraint that we've had on them was saying, okay, these nodes are fixed. That's a boundary condition. However, there could be some kinematic constraints where the nodes are allowed to move, but they can only move in a very specific order. So this is what we're going to be looking at today. So let's say that we have a nice cantilever beam here, and at the very tip of that cantilever beam, we have a node. So of course there's going to be nodes all over the beam, but let's just focus on this node right here. We said that so far we know that this node could have, let's say, a horizontal displacement u1, as well as a vertical displacement v1. So this is kind of what we did so far, and this shouldn't scare you guys. You guys saying, you know, Clayton, this is baby analysis. This is nice and easy. Not too bad. However, what happens if we take our model here and we add a rigid link? A rigid link to this beam. So what we're now doing is we're connecting the tip of that beam, or where that node is, by a rigid link to a wall. Now, the thing about a rigid link is it doesn't deform. You guys know that. So if this is the case now, the displacement of this node that we now had, which before can go in any direction, well, it's now constrained by the following path, because again, that link there is rigid, it's not allowed to deform. So this would be an example of a constraint. So how do we deal with these constraints? Well, all we really need to do is develop a constraint condition, or more specifically, a constraint equation. So in this particular case, our constraint equation would look something like this. This is basically saying that the length of that link, or the radius of that link, since it moves in a circular fashion, will always be the same. Again, it doesn't deform. So this is what we're going to be doing with these constraints. We're going to be finding a constraint equation, and that's basically it. So it sounds really complex, but it's actually going to sound more complex next slide, but it's actually not too bad at all. So this is the idea of a constraint. So if you guys are worried about this example, again, we're going to go over some examples, so it won't be too bad. But this is the idea I want to give to you guys. Sometimes we have these constraints that we have to deal with. So what we're going to be trying to cover in this section right here is, A, how do we incorporate these mathematically? I'm going to show you guys a bit of the theory. Again, we're not going to go too deep. We're going to go a nice, simple example, just so you guys can kind of understand what's going on. But I'm not going to test this on the final exam. I'll give you guys that hint right now. If I were to test one of these mathematically on the final exam, that's just a one-way ticket to have all you guys hate me. I'm not trying to do that. I want you guys to hopefully enjoy this course. Now, constraints in ABAQUS, which we'll do later, those are fair game on the final exam. Fair game. But mathematically, it's not fun. So you guys will have it on your assignment this week, as you'll see. But after that, it's not going to appear on the final exam. So how do we deal with these constraints mathematically? Well, there's a bunch of ways. The first way is directly inputting the constraint into the equation. And I'll show you guys that. It's kind of a simplistic way, but it gets really complex. So what happens in those complex situations? Well, the first option that we have is called the Lagrange multipliers method. Now, for those of you that really love math, you guys have probably seen this before. This isn't unique to the finite element method. This is a mathematical principle, and they typically use it to find minimums and maximums. However, we're going to take it and we're going to apply it to our very specific problem to help us add those constraints. So what is this method? Well, the method involves finding the minimizers of the potential energy subjected to M constraints. So the potential energy, I'm hoping you guys remember what that is. That wasn't too bad. It was just that total strain energy density minus the work done on the system. And our constraints, we're going to express as an equation. All right, so we're going to express our constraints as an equation, and we're going to have it equal to 0. And what we're going to do is we are going to create the following equation, where we have phi there is equal to the potential energy. So that term right there, we have no problem with. We covered it a lot before. And then we're going to we're going to add it to the summation of lambda I multiplied by our constraint equations over however many constraint equations we have. Now, this lambda here is called Lagrange multiplier associated with constraint Gi. So if we only have one constraint, we don't really have a summation. It's just going to be lambda 1 multiplied by our first constraint equation. Now, this creates a little bit of problems mathematically, and not so much problems mathematically, but problems for us, because if we look at this now, we actually created a bunch of unknowns. Before in our system, we were always solving for those nodal displacements, u1, u2, u3, etc. But now, in addition to solving those nodal displacements, we also have to solve all of those Lagrange multipliers. So lambda 1, lambda 2, lambda 3, all the way to lambda m. So this method is actually very accurate, but it has the problem where it can be computationally expensive. And again, there's a bunch of reasons for this, but the main one is we're creating more unknowns than our actual problem. Again, before we just had our nodal displacements, now we have our nodal displacements as well as those Lagrange multipliers. However, as you guys are going to see, the example that we're going to cover in Mathematica, it's very simple to implement this method. Very simple. On a simple scale, it's not too bad. However, another thing, it also creates numerical difficulties because the matrix in nonlinear scenarios is not positive definite. So it's going to get very messy in a nonlinear scenario, which is why we're not covering a nonlinear scenario. But this is one of the reasons why I say, typically if your model is not converging, it's typically due to contact. Contact creates a lot of problems, as you guys are going to see. So this is the first method, and we're going to cover an example to show you guys exactly what's going on. It looks really gross. I apologize for just showing it to you guys, but it's actually not too bad. The second method that we have is the penalty method. All right, so the penalty method. What we're going to do in this one, very similar to the last one, is we're going to find the minimizers of the potential energy subjected to M constraints. And you guys are saying, Clayton, that's exactly what we were doing with the Lagrange multiplier method. And that's true. Is exactly what we're going to do. However, our equation is going to change a little bit. Remember, before, our equation was the summation of lambda I, which is our Lagrange multiplier, multiplied by our constraint equation. Now it's kind of the same thing, except outside of that summation we have that 1/2 beta. Now this beta here is a penalty parameter. And basically what's going to happen is if our constraint equation does not equal 0, because remember, our constraint equation should equal 0. If it does not equal 0, it essentially penalizes that term right there because it's not equal to 0. It's basically if you're saying, if this is wrong, we're going to penalize it. Nice and simple. Now, the equation again, it looks very similar to before. We just have that 1/2 beta instead of the lambda. But one thing that I really want to emphasize a little bit later is that we can see in the constraint equation there, GI, it's squared. Please don't forget the squared. If you forget the squared, then everything gets a little bit more gross. Now this is nice and sometimes preferred over to the Lagrange multiplier method because our unknowns are still just the nodal displacements. As we can see here, we can solve for those nodal displacements U1 and U2, and that's it. We actually don't have to solve for any Lagrange multipliers, lambda I, lambda 1, lambda 2, etc. We don't need those. We just need to solve for those nodal displacements. You guys are saying, well, Clayton, what about beta? Beta is something that we as the users specify. So what we do is we specify a beta, we run the analysis, and we check the constraint equation. Is it equal to 0? If it's not equal to 0, we change beta, run it again, see if it's equal to 0. And it's an iterative process until we find a value of beta that basically enforces our constraint. So hopefully that makes sense to you guys. And again, the only trick that I've ever seen students have problems with this question, don't forget the squared sign. All right, so that's one of the things, please don't forget. Now, both of these sound very complex. I'm not going to lie. If I was in your guys' shoes and I'm seeing this for the first time, looking at those equations, I would be like, Clayton, this is disgusting. What are you doing to me? So don't worry, we're going to cover a Mathematica example, and we're going to cover all the methods, and hopefully by then you guys will go, okay, this, you know, Clayton, this isn't too bad. This makes sense. All right, so now we're going to talk about these constraints in ABAQUS. Now, the nice thing about these constraints in ABAQUS is that they're always going to follow one of the methods that we talked about. The direct method, which we're basically just throwing in that constraint and saying, you have to enforce this, the Lagrange multiplier method, and the penalty method. So these are going to be something that you guys are going to see in ABAQUS all the time. So hopefully now you guys have a better understanding of what they are. But again, you don't really have to worry about them too much. Now, what's nice in ABAQUS is if we click constraints, there's a lot of different types of constraints. All of them for unique scenarios. So the first one we're going to cover is what we call the tie constraint. So we have ABAQUS tie constraint. So constraints can be applied in ABAQUS using the constraints button in the interaction module. So remember when we were going through those modules, part, property, etc., we had always skipped that interaction because we said, well, we only have one part, it doesn't really matter. Well, inside that interaction module, we have something called constraints. So this is where we're going to actually apply those constraints in the interaction module. Now, the most common type of constraint is the tie constraint. And basically what this does is it takes two surfaces, and if they're together, it ties them together. So what it's basically saying that a node on this surface and a node on this surface, they are now tied together. So if this node displaces upwards, this node is also going to displace upwards. It essentially welds them together, if you will. Now this is really nice because the two pieces that I weld together, they don't have to be they don't have to be the same material properties. So if I wanted to, I can take a steel plate and I can put it, or I can tie it to the bottom of a concrete beam. So this is the nice part, is we can kind of fuse two parts together, but those two parts retain their original material properties. So this is how we start creating those complex models full of multiple different materials as well as different geometric shapes. Now, the question is, how do we do it? Well, it's simple. You just click the constraint button. So if you click the constraint button in ABAQUS, first thing it's going to ask you is what type of constraint you want to assign. And as I said, there's a bunch of them. But this tie constraint being the most common, it's right at the top of the list there. So we go tie, and after we click that, we basically get this menu right here. Now this menu, it looks bad, but there's only two things that you have to input and one thing that you have to consider. So if we look at the input, the interaction is completely defined by selecting two surfaces that will be tied together. That's all you have to do to create a tie. You just have to select one surface, select the other surface, good to go. That's it, nice and easy. The thing that starts confusing students is this right here. It says a master surface and a slave surface. So the master surface should be selected as the stiffer of the two surfaces or the rigid surface, which makes sense because a rigid surface technically has infinite stiffness, something like this. So your master surface should be the stiffer of the two. Now, when you're applying these constraints, it doesn't matter too much. But when we start talking about contact, this is when the idea of a master and a slave surface is going to become very important to us. So really quick, if we know that the master surface should be the stiffer of the two surfaces, let's say I want to tie a surface of steel to some surface of concrete. All right, I want to tie some steel to concrete. What's going to be the master surface? Is it going to be the steel or is it going to be the concrete? What do you guys think? Question for you guys. The concrete? Is concrete stiffer than steel? All right, so I got one concrete, one steel. So keep in mind that when we're tying two surfaces, the dimensions are going to be the same. We're tying two surfaces, dimensions are going to be the same. Because again, we're only looking at the interaction between them. If I'm tying a little steel plate to a big concrete beam, well, the interaction between them is still going to be the same. So I got more steel than concrete, it would be steel. The thing that you're going to want to look at when we're talking about the stiffness is essentially going to be the Young's modulus, elastic modulus. Steel is around 200,000 MPa, concrete's around 35,000. Steel is much stiffer than concrete. How do we make up for that stiffness in buildings? Well, that's actually going to be why shear walls are so big and steel beams are so small. So you're saying, sorry, the thickness doesn't, what thickness are you talking about, Mahmoud? Let's put it like this. Maybe this will help. If I have a big concrete plate, let's say this is my concrete right here, and this little pencil, this is my steel. If I were to touch them, then the overall stiffness of this structure is, of course, probably going to be larger because the dimensions are so big. But this whole structure doesn't interact with the steel, just that little area. So it's only the area between them that's interacting with each other. So the geometry doesn't impact anything. It's all essentially material properties at that point when we're talking about the stiffness. Does that make sense? Hopefully. All right, perfect. So that makes sense. So this is going to be the master surface. Now, if the master surface is supposed to be the stiffer of the two, then the slave surface should be the least stiff of the two surfaces. So nice and easy. Now, the thing that we have to keep in mind when we're doing this tie constraint is, again, we're taking two nodes, one from each surface, and we're basically constraining them together so that they have the exact same degree of freedom. If I were to move this node, well, this node moves with it. If I were to move this node, then this node moves with it as well. So they're effectively tied together. Now, the thing that we have to consider is this right here. It says right on ABAQUS that nodes on the slave surface that are considered outside of the position tolerance will not be tied. Now you're saying, Clayton, what does this mean? Let's say that I wanted to tie these two surfaces together and their node distribution is like this. As we can see, once I bring those two surfaces together, the nodes are essentially offset. Now, if this offset is greater than the tolerance, those nodes will actually not be tied together. So when you're tying objects in ABAQUS, you want to make sure that the nodes are very close together. So that ABAQUS says, okay, this node is tied to this node is tied to this node, etc. So how does that sound to you guys? Does that make sense? When you're tying objects, we're tying the nodes essentially. So those nodes that you want to tie, they need to be close together. If they're outside that tolerance, they're not going to be tied. It'll still be two separate surfaces. So that's going to be the most common one, the tie constraint. So again, we use this if we're doing things like welds, because it'll perfectly bond those two materials together. So that's going to be the tie constraint. The second one we're going to do is a rigid body constraint. So a rigid body constraint is actually very special to us because it's going to take a region of our model and effectively treat it as a rigid body. Why is this important? Well, this will allow us to specify rotations for our solid objects, or solid elements. Remember that we said that our solid elements don't have a rotational degree of freedom. So if I were to apply a moment, it's not going to work. If I were to apply a rotation, it's not going to work. So this is why we actually have to use the rigid body command. So what this will do is, let's say that we have a concrete beam, all right, a rectangular concrete beam. What we can do is we can take one of the surfaces of that beam and tell ABAQUS this is now a rigid surface. And from there, we're able to actually apply loads. And we'll show you guys an example, and this will make much more sense. But what's nice is we can define this again. If I were to click constraint, I get the following menu. And then right underneath tie, we have rigid body. Now, rigid body menu, a little bit more complicated. All right, it's a little bit more complicated, but it's not too bad. It's essentially two inputs again, except these inputs differ from our previous inputs. So the two things that we have to input are the rigid body region. So if I want to basically take a surface of my beam and make that a rigid body, that would be one of the inputs. And then the second one is a reference point. Now, essentially what we're doing is we're making a rigid body, and we're going to control that rigid body through a reference point. So again, I'm taking everything on my surface. Let's say that this was my surface. I say that this is a completely rigid body, and I define a reference point. So in this reference point, this is where I'm going to define all of the deformation, the displacement, the rigid body motion of this surface. So in ABAQUS, what I would do is if I were to apply a horizontal displacement at my reference point, so move it this way, they're going to move together. So this reference point is actually what's going to control that rigid body afterwards. So if we look here, this is where we select the rigid body. Now, the rigid body can be many different things in ABAQUS depending on what you want. It can be a set of elements, so a complete set of elements. It can be a set of nodes, or it can be an analytical or rigid surface. We're going to discuss what those rigid surfaces are today. So there's a lot of different things that we can pick. Now, the second input right below is that reference point. Again, this reference point is going to control the rigid body. Doesn't make sense right now, but once we do the ABAQUS example, you guys will be, oh, okay, that starts to make sense what exactly is happening. Now, before we move on, I just want to show you guys two things. Inside of the rigid body, again, we can specify many different sets for the rigid body. We can specify elements, analytical surfaces, or nodes. Now, if we look at the nodes part, we actually have two different options for nodes. We have pin nodes and we have tie nodes. And here's the only difference between them. Those pin nodes don't have a rotational degree of freedom. The tie nodes do. So let's say that I have a rigid surface and I want to apply a rotation, or I want to apply a moment, something like that. Well, if that's the case, then I need to select tie nodes. I need to include that rotational degree of freedom. If I select pin nodes, well, those degree of freedom of that rigid surface is just going to be translational. It's not going to have any sort of rotation. Last thing that you guys might be wondering, how do we put in one of these reference points? Well, of course, I'm going to show you in the example. But all you have to do in ABAQUS is go to the interaction module and then go Tools, Reference Point. Nice and simple. You guys are going to see it's a piece of cake. It's very hard to describe in lecture, but you guys will go to the example and say, Clayton, I see what you're doing. You made no sense in the lecture, but I see now. So this is rigid body, and this is typically where you guys stop. So the other constraints are more specified, but being a Civi course, so I apologize to the mechanical engineers out there, and I guess the chemical ones too, I'm going to show you guys a third constraint which many of you can find useful, which is embedded region. Embedded region. So the final constraint we'll cover is embedded region constraint, and this constraint allows us to tie an element inside of another element. So again, in the tie command, we tied two surfaces together. We said all the degrees of freedom of this surface are now tied to this one, so that the surface is going to move together. Well, this is essentially the exact same thing, except instead of tying two surfaces together, actually probably the clicker is better, instead of tying two surfaces together like this and then having them move, I'm taking something and I'm putting it inside of another object, and then they'll move together. The best way to think about this is going to be the rebar and concrete, and this is why I'm showing you civvies this exact constraint, because this is how we typically place rebar and concrete in ABAQUS. Now, if your whole goal is to look at the pullout of rebar and ABAQUS, this constraint's actually not going to work for you too well. Because when we tie nodes together, they are completely tied together. It's like a weld. There's going to be no slipping that's going to occur. So if we were to use this constraint for rebar, we're assuming full bond. Full bond. Just letting you guys know that. If we were to look at our tie menu, we can see that embedded region. It's a little bit further down the list. But once you click it, you guys have this menu right here. Again, very simple inputs. All we need to do is define the embedded region as well as the host region. And just by the names, it's pretty obvious which one is which. The embedded region is what I want to place inside of the other region. So if I have, again, a steel rebar and I want to put it inside a concrete, the embedded region is going to be my steel rebar. The host region is what you're putting something into. So in this case, again, with steel and concrete, this would be my concrete beam. So it's actually really nice and simple. All I need to do in ABAQUS, if I want a concrete beam, define the concrete beam, define the rebar, and then just tie the rebar inside of the concrete using the embedded region command. Nice and simple. Now, like the tie constraint, the nodes of each element must be closely spaced together for this to work. So let's say that I had my concrete beam with the following nodes, and I try and throw in my rebar like this. If the nodes of my rebar are offset from the nodes of my concrete, there's a chance that it actually might be outside of that tolerance. And if that's the case, then again, they're not going to tie together. So we need to make sure that when we're dealing with these tie constraints, we have it close enough together so that the nodes are actually able to tie together. So that's it for constraints. Again, nice quick theory lecture. So quick question, how are you guys feeling about constraints? We're going to cover the examples, but do you guys have the general understanding of what a constraint is? All right, I hear good. Good, perfect. That's all I want, because again, we're going to go to the theory to really emphasize what these constraints are. So I'm going to throw this down. I am going to open up Mathematica. So a new notebook over here, and I am going to bring up the question. So this is going to be the question that we are going to solve in Mathematica. And your assignment question, I'll go out. Your assignment question is going to be very similar to this. All right. And then again, after the assignment question, I will not give you any constraint type mathematics in the final exam. It's to me. So this is the question. And then I'm going to, where's my Mathematica? So we're going to solve this right here. So the example here says, find the displacement of the second node of the link. So the second node is this one over here. And it says the second node of the link is constrained such that it can only move 45 degrees on the inclined plane. So this node right here can only move in this linear line right here. It says that the Young's modulus and the cross-sectional area of the link are 10 and 1 respectively. So this is going to be my question to you guys. Remember that when we did it in the lecture here, and actually it's probably just best to pull up the lecture to show you guys. What we're basically doing is we're creating a path for U1 and U2. So in this case, this would be the kind of the arc here. But in our case, it's going to go along basically this 45-degree incline. Now, if I want to specify a constraint for this one, in other words, if I want to put a relationship between U1 and U2, what is going to be the horizontal displacement and the vertical displacement? What is going to be the relationship in this case between the horizontal displacement U1 and the vertical displacement V1? I said U1, U2, that probably made no sense. So we're going to say U1 is the horizontal and V1 is the vertical. Ah, exactly. So if it's moving on a 45-degree incline, the displacement of U1 must equal the displacement of U2. So the whole goal is we're going to solve for what this displacement is while it's subjected to that constraint U1 is equal to U2. So hopefully that makes sense to you guys. So the first thing I'm going to do is I'm just going to clear those parameters so that every time I rerun the analysis, it doesn't keep popping up as an error. And again, the first thing I like to do is specify the parameters. And I'm going to make this a little bit bigger. It's kind of small for you guys. So let's just... well, actually, I'm going to full screen it after we're done inputting the parameters. So if we were to look at the parameters here, we basically have 4 parameters. Your assignment's also going to have... well, I guess it's a little bit different. We'll discuss the assignment after. So we have the Young's modulus and cross-sectional area of 10 and 1. So I'm just going to go Young's modulus. We said that's 10. Cross-sectional area. We said that's 1. Hopefully I didn't lose you guys so far. Next thing that we have right here is this undeformed length. So the undeformed length is simply 1. So I'm going to go L naught. We're going to say that this is equal to 1. And then finally we have a force applied, which is 1. So we're going to have F is equal to 1. And those are going to be all the parameters that I need to define this problem. So before I minimize this screen over here, do you guys see where all the parameters come from, or any explanation needed before we move on? Hopefully good to go. Hopefully good to go. All right. Well, I can come back. So if you guys need this back, just let me know. So I'm going to full screen this, and let's make it a little bit bigger. So hopefully that's nice and clear to everybody. We're all happy with what we see. So let's take a little trip back to the theory and see what we're going to do. So the first way we're going to do is let's use the Lagrange multipliers approach. So we're going to solve it using both Lagrange as well as the penalty method. So we'll start off with Lagrange. It was the first thing that was in our lecture. So if we go here, basically what we want is we want to solve this equation. So this equation right here, we want to solve it for all of our unknowns. In this case, our unknowns are going to be U1, V1, as well as this lambda right here. So we need our potential energy, and then we need our constraint equation. Potential energy and constraint equation. So we're going to start off with potential energy because this is going to be the easiest of the two things. So our potential energy what is the potential energy of this system for a truss-like system? Actually, let me tell you guys this. For a continuum, for a general continuum, do you guys remember what the formula for the potential energy was? Actually, let's start off simple. The strain energy density, U. What was the formula for the strain energy density? You guys remember? Hopefully my solid mechanics people can come back and say, oh yeah, Clayton, this was it. Perfect. Exactly. 0.5. So we have basically 1/2. So I'm going to come down here and I'm going to say that U is equal to 1/2 multiplied by strain. So we'll call it E11 times S11. So essentially we have our stress over here times our strain. And this would be summed. So typically we'd have epsilon 11 times sigma 11 plus epsilon 22 plus sigma 22. But we're in a very specific case where our bar is only uniaxially expanding. So this is going to be the formula. So nice job. Now my question to you guys is, can we simplify this? Do we have a relationship between stress and strain? Do we have a relationship relating sigma 11 to epsilon 11? What do you guys think? Yes, the Young's modulus E. We know that sigma 11 is simply going to be our Young's modulus multiplied by the strain. So if I want to, instead of sigma 11, I can write this as the Young's modulus multiplied by our strain. So did I lose anybody yet? And I'm going to put this down while you guys are answering in chat. I can see that it's probably getting a little bit bright for you guys. I'll bring this down a little bit. Hopefully I haven't lost any of you guys yet. So what I'm going to do is I'm going to say, all right, I got epsilon 11 and epsilon 11. So I'd rather just write it as epsilon 11 squared. So I'm going to delete that. And then right here, I'm going to go squared. So again, to you guys, because I'm curious. This is the role of the instructor. Do you guys understand where this came from? Where this strain energy density came from? If this is crazy, you guys got to let me know so I can help explain it to you guys. Is this good to go? All right, I got a yes. Hopefully, because this is the only real trick to this question. So if we were to look at this formula for our strain energy density, U, 1/2, well, I hope you guys know what 1/2 is. It's just a number, nothing crazy. Young's modulus, well, we've already defined the Young's modulus, so that's good to go. Have we defined epsilon 11, our strain? We haven't. So one of the things that we actually have to do before we get into this part right here is we actually need to define what this epsilon 11 is. So what I'm going to do is I'm going to create a section above it. So I'm going to put strain in the link. Now, in a most typical scenario, so I'm going to, again, ask you guys this question. If I have just a bar, has an original length L naught, and I deform it to a new length L, what is my strain? If I have the original length and I have my deformed length, what is the relationship between those two lengths and the strain? Do you guys remember? What do you guys think? Do you guys know how to get strain from the deformed and undeformed length? Yes, exactly. It's going to be L minus L naught divided by L naught. So if I want to over here, what I can do is I can say that my epsilon 11, well, this is going to be equal to my deformed length L minus L naught, and then divided by L naught. The most basic definition of strain right here. Now, if we were to look at this equation, well, we have L naught twice. Oh, but that's okay. I know what L naught is. But we don't have its deformed length. So this is when we're going to actually have to create a new thing for its deformed length L. So what we're going to do is we're going to come down here, and we're going to say L is equal to, and if I were to go back to the example, which is this one, in terms of U1 and U2, do you guys know what the deformed length is going to be? In terms of U1 and U2. So not the exact solution, but can we create an equation for the length of this link? How it changes over the load? It's kind of a hard question to answer in chat. So I'm going to write something. I'm going to write what I think it is. And then I'm going to pull back up the example, and you guys tell me what you think, okay? So I'm going to say that this length is equal to the square root, because if I were to start pulling it upwards, and it has to go on that path, it's going to start creating a triangle. So what I'm going to do is I'm going to do the square root, and I'm basically going to do the formula for a triangle. So something squared plus something squared. Now, if I were to start displacing it, the amount it's going to go upwards is going to be U2. So I'm going to say, you know what, this right here, this is going to be my displacement U2. The amount it's going to go horizontally, well, that's going to be U1. So this is going to be U1. What do you guys think? Correct or incorrect? Correct or incorrect? Correct? It's actually incorrect. And that's this part right here. This should be L naught plus U1. Does that make sense? So let's show you guys over on the drawing tablet so we can kind of have a better understanding. So I'm going to share my screen over to the drawing tablet, and I'm going to share it over here. So can you guys see the drawing tablet, hopefully? So what we're going to do is we're going to say that our link currently goes from here to here. And we know that right now that this length is L naught. So if I were to take this link and then displace it to this point right here, where this is going to be U1, and I were to also displace it upwards to this point, because remember, it has to have that 45-degree angle. So this is U1, and this is U2. Well, then my triangle is going to look something like this. So now do you guys see where the L naught plus U1 comes in to play? I'm hoping that this makes it nice and clear to hopefully everybody. So this is going to be the thing of the link. Now we actually have a constraint between U2 as well as U1, but we haven't applied that yet. That's where the Lagrange multipliers are going to come into play. But in the general sense, the length of this link in the deformed case, as expressed by the displacement of U1 and U2, can be defined by that equation that we now have in Mathematica. So I'm going to switch the screen back over to here. So hopefully we're all back in Mathematica nice and happy. And we can say, all right, well, now that I have my length, I have my strain. Now that I have my strain, I have my strain energy density. But remember that when we're dealing with the virtual work, and not virtual work, the Rayleigh-Ritz, that's an approximation method. When we're dealing with potential energy, we're actually dealing with the total strain energy. So this is the strain energy density. But what I need to do, just like we did for beams, is I need to actually integrate this over the length of the beam. So I'm going to say my total strain energy is actually the integral of this strain energy density over the length of the beam, or I guess in this case the length. So x1 from 0 all the way to L. I guess in this case L naught, because we're dealing with the original length. So this is going to be our total strain energy. That's kind of the first term that we need. The second term that we need is going to be the work done on the system. So let's see what you guys remember. What is going to be the work done on this system right here? Work done on this system. Go ahead and take a guess if you guys are unsure. This is the whole part, is we're all having fun here. So I got a private message that says P, or I guess in this case F, multiplied by delta L. So yes, but what is delta L? So we need to express everything in terms of U1 and U2. So what is going to be the work done on this system in terms of U1 and U2? Yes, exactly. So I got a private message. It's going to be our force multiplied by U1. So force multiplied by U1. Nice and simple. So this is going to be good to go. So at this point, we actually have our potential energy. Because remember, our potential energy is simply going to be our total strain energy minus the work done on the system. So if we didn't have any sort of constraints, this would be able to solve our problem. We are good to go at this particular point. Problem is, well, we actually have those constraints. So we're actually going to need to change things a little bit. How do we change things? Well, we are going to go, and I'm just trying to find where the PowerPoint went. Oh, here it is. So we've now covered this term right here. Now we need to get into this term. So my first question to you guys, how many constraints do we have? How many constraints do we have? How many constraint equations do we have? That's the best way. How many constraint equations do we have? In this particular problem, how many constraint equations do we have? u2, we actually only have 1. So the constraints, we're not talking about the boundary conditions. We have one constraint equation, and that's u1 is equal to u2. That's it. That's all. u1 equal to u2. Nice and simple. So what we're going to do is we're going to create that constraint equation. So u1 equals u2. That's this part right here. This is the constraint equation, gi is equal to 0. So if we know that u1 is equal to u2, we can create this equation equal to 0 by saying that u1 minus u2 must be equal to 0. Hopefully that makes sense to you guys. And this right here, this lambda, this is something that we're actually trying to solve for. So what I'm going to do is I'm going to create a new section called Constraint right here. And we're going to say our constraint equation. So I'm just going to call this Constraint. This is going to be u1 minus u2. Now again, this constraint equation must be equal to 0. If it's not equal to 0, then u1 does not equal u2, and our whole constraint is violated. So this is what we're going to have right here. So if we want that phi, that big equation phi that we have right here, all we need to do is take our potential energy and then add it to this constraint that we have. So I'm going to call it phi. This is going to be equal to our potential energy that we did before. And we're going to multiply it by lambda, multiplied by our constraint equation. So all this is right here, if we were to go back to the PowerPoint, which I always seem to lose, that's just this plus this part right here. Why is there no summation? Well, we only have the single constraint. If we had many constraints, then we have to do lambda 1, lambda 2, lambda 3, etc. So now the whole goal here is going to be minimizing this equation. Remember, in the Rayleigh-Ritz method, we took our potential energy, we minimized it, and then we solved for u1, u2, u3, however many unknowns that we had. Well, mainly in beams, we'd solve for those A coefficients. But we're going to do the exact same process now, except instead of the potential energy, we are now going to minimize this phi. So I'm going to create a new section. I'm going to simply call it minimize. And we're going to create equations for each one of our unknowns. Now, if I were to run this right now, and I'll show you guys, but how many unknowns are we going to have in this equation phi right now? How many unknowns? What do you guys think? How many unknowns? Three? That's exactly correct. We have u1 and u2, and then we have lambda. So 3 unknowns total. So we're going to actually have to make 3 equations. So I'm going to say my first equation, not equation 2, if it's my first one, is going to be the derivative of phi with respect to our first unknown, which we know is u1. I'm going to repeat the exact same thing for our other 2 unknowns. So I'm just going to copy it, come down here, and instead of u1, this one we're going to do u2. Instead of u1 and the third one, we are going to do lambda. So all I'm doing is I'm taking the derivative with respect to each one of our unknowns. In this case, we have 3 unknowns. So then what I'm going to do is I'm going to solve the system, because we know that this equation here must be equal to 0. This equation here must be equal to 0. And this equation here must be equal to 0. So that's what we're going to do. So I'm going to go solution is equal to find root, because they're all going to be equal to 0. And this find root command is very similar to the solve command, except it's better for nonlinear cases. As you guys will see, this find root command, it's actually more of the Newton-Raphson method, where we provide an initial guess. So we're going to have 2 inputs, and they're going to be separated by those nice squiggle brackets, just like the solve command. The first one is going to be what are our equations and what are they equal to. So we know equation 1 equal to 0, equation 2 equal to 0, and equation 3 equal to 0. Hopefully that makes sense. The second one right here is going to be what are the unknowns. But the nice thing is we can actually provide initial guesses for those unknowns. So inside of the squiggle brackets, I'm going to have another squiggle bracket, and I'm going to say my first unknown is u1, and I'm going to say it has an initial guess of, let's say, 0.01. Again, those are just an initial guess. Come down to the next one, we have u2. I'm going to say, you know what, maybe this also starts around 0.01. And then finally, our third one is going to be lambda. And we're going to say that lambda, maybe it starts at around 1. So if I were to run this really quick, I get this right here. U1 is equal to 0.089. This would be units, millimeters, meters, whatever. U2, as we can see, is the exact same. It's the exact same. So in this case, this is what we have for our first one. And I didn't suppress this part right here, so I'm just going to go up right here, suppress it. So this is going to be the Lagrange multiplier method. Is there any questions about this? Any questions about the Lagrange multiplier method? What do you guys think? It's not going to get more complex than this. Your assignment is actually... So are those good common first guesses? It's usually, like, you don't have to be too good with these first guesses. The find root command is very powerful. But yeah, I would just go 0.01 or 0.1. Go up by increments of that 1, if you guys will. It usually won't be a lot. It's pretty simple to see that if we were to go back to our problem, if the original length is 1 and we were to apply a unit force, chances are it's not going to fly over to 100 millimeters of displacement. If our original length is 1, that's a lot of stretch, if you guys will. So it's usually based on the problem. So hopefully you guys are good with the Lagrange multipliers method. Now we're going to do the exact same thing, except we're going to do the penalty method. Exact same thing, except we're going to do the penalty method. So I'm going to switch this right here to penalty. As you guys are going to see, penalty is almost exactly the same. So we're just going to use the same code and we're going to switch it. The code that I provided on eClass has all three separated. So you guys can see all three, but for the purpose of this example in person, we're just going to go through this. So the first thing, is this description of the length of the link going to change? Is this dependent on our current constraint? What do you guys think? Is this length going to change? The way we describe the deformation of this link? No, exactly. So if the length doesn't change, well, our strain formula doesn't change. If we were to look at our potential energy, it's based on the strain, which we said doesn't change. So basically, all of this stays the exact same. That's nice for us. And this is shown in the theory too, because if we were to go down now to the penalty method, our first part, potential energy, it stays the exact same. Where it starts getting different is going to be this constraint part right here. So now we're going to look at the constraint. My constraint equation, U1 minus U2, which is of course equal to 0. Does that change between methods that we're using? This part right here. Does our constraint equation change? No, exactly. It doesn't change either, because no matter what way we're solving this problem, we always want U1 equal to U2. It doesn't matter the method which we're solving. So this doesn't change right here. What changes is going to be this part right here. So in the Lagrange multiplier method, we have lambda multiplied by our constraint equation. In the penalty method, we had 1/2 multiplied by beta multiplied by our constraint equation squared. So this is going to be one of the things where, again, please don't forget the squared. This will get you. So as we can see in Mathematica, beta is undefined. Now beta, again, is something that I want to reiterate. We don't solve for beta. This is something that we input as a user. So what I'm going to do is I'm going to come up here for the penalty method, and I'm going to say beta is equal to 1. Again, this is something we specify. What's going to happen is we're going to solve it. We're going to get U1 and U2, and we're going to compare how close they are. If they're still not close, then we keep increasing beta until they come together. We keep penalizing it until our constraint holds true, basically. So if we were to look at this equation right here, we have our potential energy, we have 1/2, we have beta, and then we have our constraint. So how many unknowns are in this equation now? How many unknowns are in our new equation? Yes, I got a direct message. We have 2. Before we had 3, we had U1, U2, and the lambda. But now we don't have lambda, so we just have U1 and U2. So this part right here where we're minimizing, it's going to be the exact same thing, except all I'm going to do is remove the lambda term, and in turn our equation 3 term. So if I were to run this right now, I have u1 is equal to 0.0945 and u2 is equal to 0.05. As we can see, u1 does not equal u2. So what do? We penalize the sucker. We come up to beta and we say, you know what, if you don't want to work, we're going to have a bigger penalty. If I were to run this again, we have u1 is 0.09 and u2 is 0.0823. So they're getting closer, but they're still not exactly the same. So you know what, I'm going to look at that and say, I'm going to penalize you again. Go to beta, make it 100. Run that bad boy. As we can see, they are starting to get closer and closer together. So it's an iterative process where you keep penalizing it, and then at some point, they become equal. So how does that sound to you guys? Does that sound good for the penalty method? As you guys can imagine, it gets pretty difficult because the potential energy of nonlinear systems gets a little bit gross. So this is why we're keeping it simple, and this is why I'm not putting it on the final exam. You guys will have it in your assignment. So actually, this would be a good time to show you guys the assignment. So if I were to open up assignment 8, which will be your last experience with this method, this is the problem right here. We have the exact same link right here, and it is constrained by the following path defined by this ellipse right here. So before we said that u1 is equal to u2, here we can get our constraint because the equation relating u1 and u2 can be defined by this ellipse right here. And that's it. Everything else is going to stay basically the exact same. Just download the code from eClass, define your new constraint equation, and then basically set the parameters up. So as you guys can see, nice and simple. We're not going to get too crazy on this theory. So how does that sound to you guys? You guys, so you know, St. Clayton, this is pretty good. I'm glad I don't have this in the final. All right, so we're going to take a little bit of a break. So let's say until 9:10. I'm going to go refill my water, use the little boys' room, all that fun stuff. And then we're going to come back and we are going to do an ABAQUS example. Because I know you guys are here for the ABAQUS examples. You guys don't care about the Mathematica, let's be honest. So let me just show you guys the example really quick. This is what we're going to do in ABAQUS right here. So we're going to create a 3D shape. 3D shape. I haven't done that with you guys yet. As you guys are going to see, it's very simple. But we're basically going to have two parts right here. We're going to have a base plate and we're going to have a column. What we're going to do is we are going to tie these two together at this interface down here. And then we are going to apply both a displacement as well as a rotation. Now, before we go really quick, could I apply this rotation if these were regular solid elements and I didn't use any constraints? Could I apply a rotation without any constraints if I were to use solid elements in this scenario? Yeah, I got a private message. I can't. What I would have to do is figure out the displacement of these nodes to kind of manually twist it, which sucks. No one wants to do that. So this is going to be the example we do when we get back from the break. So I kind of talked a little bit. How about we make it 9:12, and then we're going to come back and do this ABAQUS example. So again, I'm going to just go refill my water, stuff like that. If you have questions, throw it in the chat, and I'll answer it when I get back. All right, I will see you guys at 9:12. All right, guys, I'm back. Are you guys ready for the ABAQUS fun? All right, so again, this gets really weird switching between screen sizes. So this is going to be the example that we're going to cover, and there's no contact yet, but this will show you guys how we implement the constraints. So it says, assuming the left side of the surface of the base is fixed, so this side kind of over here, move the top surface of the column horizontally by 100 millimeters and rotate the surface by 90 degrees. And then it says remove the displacement and rotation in the second step. So this is going to be kind of a first because not only do we have two parts, but now we actually have two different steps. So it's going to be a lot of fun. It says the dimensions of the base plate and the column are this, and they are welded together. So if they're welded together, then we can use that tie constraint to basically hook them together. It says the Young's modulus of the Poisson's ratio of the material is 200,000 MPa and 0.3 respectively. And it says that the material yields at 400 MPa and has an ultimate stress of 600 MPa at an ultimate plastic strain of 0.03. So my question for you guys really quick. If it gives us the stress corresponding to a plastic strain, do we need to modify any of that in our material parameters? What do you guys think? It gives us a plastic strain already, so do we need to modify any stresses or strains? No, exactly, we don't. So what we're going to do is, the first thing I'm going to have to do is create the parts. So this is where it's a good idea to show you guys how the parts is different than the assembly tab. We always had one part before, so our assembly tab was simply just the part. But now we actually have two parts. We're going to create this base plate here, and then we're going to create this column up top as two different parts, and then in the assembly tab we're going to throw them together. So our base plate is 200 by 200 by 10, and the column is 10 by 10 by 200. Minimize that, and we're going to start off with our parts tab. So I'm going to click this part right here, create part, and we are going to start with our base plate. So I'm just going to call it base. Why not? Now the difference where things come in is, instead of going 2D as we typically do, we're sticking in 3D. All right, now we're in 3 dimensions. So there's a couple different ways we can do it. One is we can do an extrusion, which basically we create the cross section and then we can define its length afterwards. We can do revolution, which basically means we can define a part of it and then it'll revolve it in by 360 degrees, so like a pipe. Or then we have sweep, and that one's a little bit more complicated to describe. So we're going to stick with extrusion. So all we're going to do with this extrusion is we're going to create some of the cross section, and then we can specify the depth. So we're going to go 3D, deformable, and extrusion. Continue, and we're left at this same 2D menu that we had before. Again, when we're doing this, we are just defining the cross section. So what I'm going to do is I'm going to use this rectangular command right here again. I'm going to start off at 0, 0, and we are basically going to create one of the sides of that base plate. So we said that the side is 200 long and just 10 millimeters going to the top. So I'm going to go 200 by 10. If I were to do that, I get this right here, which is one of the sides of that base. So after that, I'm saying, well, you know what? That's all I need. I'm good to go. I'm going to go done. And once you go done and you're doing 3D, it's going to say, all right, well, so what's that depth into the page? Well, if I model this side, then my depth into the page is going to be 200. Nice and simple. I go, okay. I now have my base plate. It's funny because people think 3D models are a lot more complex, but they're actually not. They just take longer to run. So this is going to be my first part. Now, again, unlike our previous models that we've done, we actually need 2 parts. So we have our first part, we're good to go, but we need to create a second part, and we're going to call this one the column. Again, it's going to be 3D, and we are going to use the extrusion type to basically just define its in-plane depth. So I'm going to go OK. And we said that the cross-section of our column was 10 by 10. So I'm going to, again, use the nice rectangular command here, start off at 0, 0, and I'm simply going to go to 10, 10. Just like that. So you know what, that's good to go. And it says done. And we have to specify the depth of that column. Well, we know it's 200 millimeters in height. So I'm going to go OK. So now I have 2 different parts. If I were to go to this last part over here, we can go from column, back to our base, back to our column. So now we have our 2 different parts. We haven't assembled them yet, but we have our parts created. So just really quick in the chat, is that good? Are you guys concerned about creating the parts, or is that not too bad at all? I'm hoping good. I miss in-person lectures when I could put people on the spot. That's always so much fun. All right, so parts, good to go. Move on to the next tab, assembly. Or sorry, property. We'll get to assembly later. So now that we have our 2 shapes created, we need to assign it some material properties. So what we're going to do is we're going to go over to our create material property command, and we are going to define the material. Now the nice thing for us is both the base as well as the column, they're the exact same material. So we only need to create one material type. And we're just going to simply call it steel because the properties, they're very similar to steel. So we have our elastic properties. So I go mechanical, elasticity, elastic. And the question says that the Young's modulus was 200,000 and the Poisson's ratio was 0.3. Again, this comes right from the question. So if I were to pull this up, pull up our question. We said Young's modulus right here, 200,000, Poisson's ratio, 0.3. Now when it comes to the plastic properties, it says the material yields at 400 and has an ultimate strength of 600 at a plastic strain of 0.3. I say, all right, well, that's not too bad to implement. I go mechanical, plasticity, and then over to plastic. And it says the yield stress was 400. What is the plastic strain at the yield stress? What is the plastic strain at the yield stress? I got a private message saying 0. Completely correct. We have 0. And then our ultimate stress was 600. And it said that the plastic strain was at 0.3. So now we have all of our material properties good to go. So if I were to expand this, I see that my steel material is now defined. Now the next thing we have to do, just like before, is we have to define a section. So we can go right here to create section. And we're just going to call this our steel section. Nice and simple. It's homogeneous. We go continue. And the material says steel. And we still have this button that says plane stress / strain thickness. Well, we can just ignore that. We go OK. And we have our section. So now that we have our section, we can take it and apply it to our parts to give our part that material property. So I'm going to come right here to assign section command. It's going to say select the region to be assigned to section. Well, I want my column to have that section. So I'm going to go column, good to go. What section? Well, I only have the one defined, so I'm just going to go OK. Just like before, if it turns that nice green color, we know that it's good to go. So our column is good to go, but if I were to go back to our parts and go over to our base is not green. We applied it to our column, but we haven't applied it to our base. So we have to come over to our base, do the exact same thing where we go assign section, select the region. Well, I want my base right here. I go done. And what section do you want to apply? Well, again, we only have the one. I go OK. Now they are both green. So now both of our parts, column as well as base, have the material properties defined. So we say, all right, well, we're good for properties. Let's go to assembly. And now this is where things are also going to start to change, because again, before we only had one part. So once we imported it, we were always good to go. Now things are going to get a little bit different. So just like before, we need to import our parts. So we're going to go create instance right here. And it says select the parts you want to create. So now we have two parts because we have two different ones. We're going to import our base first. So we're going to go apply. So now we have our base in. But we also want to import our column. Now, one of the nice commands that we have is we can click this auto offset from other instances just to kind of make it a little bit of parts. We say, all right, that's good to go. We can go OK. So now if we were to go to our assembly tab right here, under instances, as we can see, we have two different instances selected. So this is how we bring them both in. But now we have a problem because, of course, our model that we want to do, it doesn't look like what we have. We need to somehow bring this column up to this corner over here. So this is going to be our next goal. However, as you guys are going to see, that's actually rather simple. So what we're going to do is the first thing we say is, all right, well, the base plate itself, it's good to go. The column needs to be rotated, though. The column right now is horizontal. We want to swap it so that it's vertical. So what we're going to do is we are going to rotate it. So if we were to go right here, we can see that there is a rotate instance button. Rotate instance button. So what I'm going to do is I'm going to click that button, and it says select the instance you want to rotate. Well, I know I want to rotate my column, so I'm going to select my column. It's nice and selected. I'm going to go done. Now it says select an axis or a start point for the rotation. Because remember that instead of just rotating it so that it's upwards, we can also rotate it so that it's going the other way or going this way. So we always have to specify what axis we want to rotate about. Well, we know that we want to rotate kind of around this axis right here, which is the x-axis. So all I'm going to do is I'm going to pick the 2 points on my column corresponding to that axis. After I'm done and I've defined that axis, it says, how much do you want to rotate it? Well, I want to rotate it 90 degrees. I go OK. And as we can see, our column is now rotated 90 degrees. And now this is where it kind of gives you a, is this what you meant to do? So you have to confirm that this is what you meant. So we look at this, we say, yeah, that's what I want. Okay. Nice and simple. So now as we can see, our column is orientated the right way, but it's still at an improper location. Remember, we want this column to be on top of this base plate over here. How do we do that? Well, we go over to this button right here, Translate Instance. So we have Rotate Instance, but we also have Translate Instance. Same thing as before, select the instance you want to translate. Well, that's going to be our column right here. Good to go. Go done. And it says select the start point that you want to translate. Well, what I want to do is I want to move this corner. Actually, let's zoom in more. I want to move this corner up until this point over here. So it's actually nice and simple. I'm going to select this corner, and then it says select the end point. So I know I want to move this corner up to over here. So I just simply click it. Our column is now moved into the correct spot. And again, it'll ask you, is this what you wanted to do? This is when you go, okay. So now in terms of assembly, we are done. We have exactly the model that we wanted. So is there any questions thus far? You guys still feeling pretty confident? Still feeling confident? Maybe not. Hopefully. I hope you guys are anyway. All right, so now we're going to say our assembly is good to go. Now we have to define our steps. So I already kind of hinted, we actually have two steps in this case. The problem wants us to apply the load, and then it wants us to remove the load. So those are definitely going to be two different steps. So I'm going to click my Create Step button. Our first step, we're going to call it Apply Load. Makes sense. You always want to name your step what you're doing so you don't get it confused. It's going to be after our initial step, and it's going to be just static general. So I'm going to go OK. We are popped up with this menu right here. Nonlinear geometry. What do you guys think? You guys want nonlinear geometry on? You guys want? Should we click nonlinear geometry on? Yes, we should always click nonlinear geometry if we're dealing with a nonlinear problem. So nonlinear geometry is on. And in incrementation, I'm just going to add some increments. I'm going to set my maximum increment to 10% and my initial increment to 10%. And I'm going to lower the minimum just because we're dealing with plasticity. Just in case it hits that minimum threshold, we don't want it going too far down. So I'm just going to change those. I'm going to go OK. And that's our first step. So if I were to go to my steps, we have our initial step. We have our apply load step. But now we actually have to create another step. And this is removing the load. So what we're going to do is we're going to create a second step. And in this step, we are going to say remove the load. We're going to go continue. And as you guys will see, if you guys have nonlinear geometry activated in a previous step, it'll always have to remain on. We don't even have the option to take it off anymore. So we're going to have it on by default. Incrementation, I'm just going to change these to the exact same as what I had in the previous step. I may not need all these increments, but it's better to have it than to run it halfway, have it abort, and then have to rerun it again. So now I have my three steps. Initial step, boundary conditions, that's where they go. Our applied load step, so this is where we're going to apply our load, and then remove load. So this is where we just simply remove the load. So far we've done everything that we've done in previous lectures. We added some stuff like an additional part, an additional step, but these modules right here, they're nothing new. They're nothing new to you guys. You guys should be thinking, you know, Clayton, this isn't too bad so far. Quick little water break. All right, so is there any questions thus far on the stuff that we've already kind of dabbled in before? Any questions before we get into the new stuff, which is going to be our interactions? All right, I'll take the silence as a good thing. Again, you just interrupt me if you guys have any questions. So again, we always said that interactions, we never had them. We skipped this step. We went right into loads. Well, now we have interactions. So really quick, just out of curiosity, how many interactions do you think we have in this model? How many interactions do we have to define? How many interactions do you guys think we have to define in our model over here? 4? What would be the 4? I'm not sure what you mean by each corner, but the answer is, as Mahmoud said, we have 2. Our first interaction is tying this surface to the bottom of the column. That's going to be one of our interactions. The second interaction that we have is we're going to take this top surface and we're going to make it a rigid body so that we can apply that rotation to it. So does that make sense to you guys, why we have 2 interactions? Does that make sense, hopefully? All right, perfect. So which one do you guys want to do? Do you guys want to do the rigid body first, or do you guys want to do the tie first? Completely up to you guys. And it doesn't matter which order you guys do them in. Rigid body or tie, up to you guys. I'm using this as an excuse to rehydrate. All right, you guys aren't picking any, so we'll do the easy one first, since you guys don't want to pick. I offered. So we're going to do the rigid body first. So what we're going to do is we're going to make this surface up here a rigid body. And the reason why is because then we can start applying rotations to it nice and simply. So what we're going to do is we're going to go to the interaction module. And this button right here, this is where the constraint is, where we're going to want to create those constraints. I'm going to scroll down here so you guys can see. It's kind of in between our step and our load. We have contact controls, constraints, interactions, interaction properties. This is where we're going to be playing with a lot today. Now remember when we said when we're creating a rigid body constraint, we take a rigid body and we tie it to a reference point. And we apply all the displacement at that reference point. So the first thing that we actually need to do if we're doing a rigid body is we need to create a reference point. So there's 2 ways of doing this. The way I showed you guys in the theory was going up here to tools and then going reference point. That's one way. If you guys prefer buttons, then it's just right here. RP reference point. So I'm going to click this and it says, where do you want to put this point? Well, I'm just going to put it right here. It doesn't really matter too much where I put this point. So now I have my reference point defined. I can actually start creating that contact or that interaction. So what I'm going to do is I'm going to go to contact or constraints right here, double click it, and then we get this menu. So this is the menu that you guys had in your theory slides. So if I want to, instead of going constraints, I can go to this button right here, create constraint, same menu. So now what we're going to do is we're going to call this our rigid body constraint. So rigid body. And of course, we are going to use the rigid body constraint. We're going to click continue. And then we're given the menu that you guys had. So again, we want to define 2 things. The first one is going to be what is the surface that's going to be our rigid body? And the second one is what is our reference point? We'll start off with a simple one, our reference point right here. We're going to select it. And we only have our 1 reference point, so we click it. And now it says a reference point is picked. So that's good to go. The second part is we have to select that surface or the region that's going to act as a rigid body. So we want all of the nodes on this right here. We want all of the nodes on this surface to be our rigid body. And we said for nodes, we have 2 options. We have pin or we have tie. So if you guys, let's see how well you guys remember. If I'm doing a rotation on the top of this column, do I want the pin or the tie command? Which one should I pick? Oh, you guys are quick. So I got a private message, so you guys can't see it, but tie, that's completely correct. Remember that tie has that degree of freedom in the rotation direction, or a rotational degree of freedom. So if I were to go pin and then apply a rotation, well, it's not going to work. So we actually have to go tie over here, and then we click this big button here to basically select our region. So what we're going to do is we're going to select this surface over here. We are going to go done. And therefore, we now have our region picked. We have our reference point picked. We're good to go. So constraints in ABAQUS are always represented by these little circles. So if you guys have those little circles, it means that you're good to go. Your constraint is defined. And what we essentially did there is during our analysis now, this surface is going to be a rigid body. So all of the nodes on this surface are going to stay in the exact same position as we deform it. Now, our beam itself, this can be deformable. This can deform as much as we want. It's just these nodes on this particular surface that are going to remain constant distance from each other. So that's going to be our first one. Now, the tie command gets a little bit different, and it becomes a little bit of a pain in the ass, as you guys are going to see. I kind of tricked you guys a little bit. So for our tie command, if we were to click it and then we were to go tie and go continue, it wants us to select the surfaces. So if I were to say, all right, well, the master surface, let's make that the base. They're the same stiffness, so it doesn't matter. So I say, all right, that's going to be the base, done. And it says, all right, the slave surface, well, that's the bottom of the column. Oh, wait. How do we select the bottom of the column? So this is where, when we're defining tie constraints, and more specifically, once we get into contact as well, we typically want to define the surfaces in the assembly module, so that when we come over here, we can just click them, if you know what I mean. Well, you don't know what I mean. So let me show you what I mean. So instead of going into our interaction, let's go back to our assembly. If I were to go to my assembly tree right here, I have sets and I have surfaces. So what I can do in this tree is I can already create the surfaces that I know I'm going to apply contact to. So what I'm going to do is I'm going to create a surface, and I'm going to say, all right, this is going to be the surface of my base. I'm going to go continue, and then from right here, I'm going to click it and go done. So right here, I already have my base nice and defined. I'm going to do the same thing for the column. Now, what's nice here about the column is when I'm in the assembly module, I can take my base, I can right click it, and I can suppress it. It doesn't delete it. It's still there, but it's hidden. And what's nice about this is now that it is suppressed, I can come underneath and I can create a surface for the column. So my column surface, continue, and I can select the base of this column now. I'll zoom in right here. I selected it. I go done. So now what's nice is I can go back to my base that I have defined. I can right click and I can now unsuppress it. So I can go resume. I now have this back, but what's nice is I now have my surface still defined. So if I were to come over here and zoom in, if I were to go to my surfaces, I have my base surface and I have my column surface. They're already defined. So now when I go down to my interaction again, I'm going to go to the exact same thing I did before. I'm going to apply a constraint. It's a tie constraint. And what I'm going to do is I'm just going to call this tie, nice and simple. But now when I'm selecting the surfaces, I can go, all right, my master is going to be a surface, but rather than actually selecting it from the viewport, I can go over here to surfaces and I can select my previously defined surfaces. So I'm going to highlight it in the viewport to kind of reassure me what I'm selecting. So I created a surface for the base. Perfect. I go continue. It says, what is our slave type? Well, that's also going to be a surface. Which one do you want to pick? Well, I already defined a column surface. As we can see, it kind of went a little bit more purple than the red. I can go continue. And this basically says, I'm tying this base surface to the column surface. Good to go. It's good to go. So we click continue. And again, we have those circles that appear, which basically tell us that the constraint is defined. So now we have our two constraints defined. We're good to go. So our constraints now are actually good. Is there any questions about constraints? How is that? Any questions about constraints? Anything that was confusing to you guys? Is it possible to select the reference point as the centroid of the surface? So I'm not sure if you guys saw it, but I think it was a direct message. It is possible. So when I select the reference point right here, it says that I can enter the XYZ. So if I were to know where that location is, I can just enter it as an XYZ location. Good question. That's a really good question. All right. So now that we have our constraints defined, we can say, all right, interaction module is good. We can go to our load module. So the first thing that we're going to do is apply our boundary condition, because that's always the most simple. And we said in this particular problem, we are fixing, I want the surface. We're fixing this surface. So all we're going to do is we're going to create a boundary condition just like before. And we are saying fixed surface. The step, since it's a boundary condition, we're going to throw it in the initial step. And this is a displacement or rotation boundary condition. So I'm going to go OK. I'm going to select that surface that we want, go done. And I want to restrain it from displacing in all three directions. I go okay. As we can see, this is now fixed. It's good to go. Now, what we want to do is we want to apply the load at our rigid body. So we're going to apply the load at our reference point. So now we're going to create another boundary condition, but this is actually our displacement. So this will be in our apply load step. We're going to call this our displacement. We know it's also a rotation too, but we're going to call it our displacement. It's going to be displacement and rotation. We're going to go continue, select the boundary condition or the location. Well, we're going to apply it to our reference point right here. We're going to go done, and it's going to give us this option right here. So again, we want to apply a horizontal translation of 100 millimeters in the x direction. So as we can see, our x direction is going this way. So we're going to go U1, 100. And then we also want to rotate this surface by 90 degrees. So if I want to rotate this surface, oh, I guess it's kind of hard to tell. I want to rotate about the z-axis. It's kind of, I couldn't define it too much to show you guys. Now, if I want to rotate it 90 degrees, how many radians is 90 degrees? How many radians is 90 degrees? Pi over 2. So you think in ABAQUS I can throw that in? You guys know what it is though, so it's good. So we're going to go around 1.57. Now I'm rotating it negatives just to make sure that it goes this way rather than, well, I guess I can do it, rather than this way. So just negative 1.57, good to go. So as we can see, we have our displacement and then we have a rotation about that axis. So that is going to be our loads, nice and simple. Now my question for you guys, applying the loads, I know you guys are experts at it. You guys are saying, Clayton, come on, give me a challenge. Here's your challenge. We applied the loads. How do I remove the loads? What do you guys think? How do I remove the loads? So have them in the opposite direction. That's a good guess. But the problem is if I apply a displacement of 50 millimeters, and then in the next step I apply the displacement of 50 millimeters back, in the step, this 50 millimeters pulling is still going to be active. So what's going to happen in that step is you're going to have it pulling in both directions. It's actually much simpler. This is kind of one of the funny things. Sorry, I'm just reading. Make another load and put 0 for the rotation and the displacement. So that's, again, what's going to happen, as Sabrina said, where it's going to start pulling in opposite directions. But Adam is correct. We're going to deactivate the force. It's as simple as that. So what we're going to do is we're going to go to our boundary conditions where we applied our load. Or if we had a load like kilonewtons, we'd go to our loads. But in our boundary conditions, we're going to right-click it, and we're going to go Manager. Right-click it and go Manager. Then we get this menu right here. As we can see in our initial step here, our fixed surface, actually let's try and expand this, our fixed surface was created. Now what propagated means is it means it's still going to be active. It's still going to be active. So what happens, we create our fixed surface and it's basically maintained through all of the steps. Now, our displacement, we created that displacement in our apply load command, or step, I guess, and then here it's propagated. So this means that after, in step 2, it's still going to be there. So what we need to do is we're going to take this, and instead of keeping it propagated, which means keeping it active, we're going to deactivate it. And this is all we have to do. This is all we have to do. And the reason why we don't apply the load going in the backwards direction is this. If I were to take my pencil, all right, I'll zoom up nice and close. You guys can see my homeless looking beard. If I were to take my pencil, oh, I guess there's the camera, and I were to displace it to this point right here, and it's plastic. So if I were to displace it to this point right here, and I apply the opposite direction, so I displace it 50, let's say, and I put it back to 50, that's a problem. Because if I were to take it, displace it 50, and just let it go, it's not going to go back to 0. If it's plastic, it has that permanent strain. So once I just let it go, it's going to come back up, but it's not going to go back to 0. If I were to displace it back to 0, well, then I'm almost doing a cyclic behavior on it. I don't want to do a cyclic behavior. That's why we just let it go. We keep it inactive, and we say, good to go. Does that make sense to you guys? Why we don't want to push it back? Because then we're doing the cyclic behavior. Hopefully. Yes, perfect, perfect. So I'm going to right click, go manager, just double check, good to go. So now we have everything defined in our loads. We can go to mesh. So what I'm going to do is I'm just going to apply a similar mesh to both. And it's funny because now I can finally show you guys. So when we're applying the mesh, I always said we have to go from assembly to part. And this is why, because we can't mesh this all at once. What we need to do is we need to mesh our individual parts. So we're going to start off with the base. And let's just check the question really quick. Blah, blah, blah. All right, so it doesn't say, but we are going to use, well, it doesn't say. What do you guys think? Should we use plane stress or plane strain? Yes, so my acting was terrible, and I'm glad my mood picked up. It's 3D. Remember, plane stress and plane strain only apply in 2 dimensions. Only apply in 2 dimensions. For 3-dimensional shapes, we don't have plane stress or plane strain. So thank you for picking up on that. That was great. I was hoping somebody would. Well, actually, low key, I was hoping somebody would say plane stress or plane strain. So, but you guys were too smart. So what I'm going to do, I'm going to seed my parts. I'm going to put an approximate seed of, let's go 3.33. And I'll show you why I'm doing 3.33. So I'm going to go apply, okay. And then basically we're going to keep everything default. We're going to use linear with reduced integration. You notice how it's 3D stress. So up here, there's no plane stress or plane strain. It's simple 3D stress. We go okay, and I'm going to mesh it. So the reason why I picked 3.33 is so that I have 3 elements going up here. So when I go to my column now, I got to go mesh that bad boy. What I'm going to do is I'm going to seed it. I'm going to pick the same seeding, so 3.33, apply it, and then I'm just going to mesh it. So the reason why I picked 3.33 is because of this. I want to keep the nodes of my column close to the nodes of the base plate. Remember, if these nodes are far off, they may not mesh, or they may not be tied together. So this is why I want to keep the mesh size consistent going through the parts. Now, advanced mesh techniques would be a little bit different, because what I would do is I'd pick a smaller mesh in this area to keep that tie nice and close, but I would pick a much larger mesh in this area because nothing's really going on. This is kind of overkill, but if you guys are looking for a simplistic way of doing it, this would be a valid method, if you guys will. So this is good to go. We look at our mesh, good. We can go to job. So let's call this constraint test. Why not? Continue. It's 3D, it's a little bit beefy, so I'm just going to pump it up just a little bit. And we can run this bad boy. So watch it abort, and I have no idea what happens, but let's just see what happens. Submitted. Of course, we can monitor it to see what exactly is happening. Oh, it's running now, which means it accepted. And let's just see how fast it goes. As you guys can imagine, once we start getting into 3D, everything gets a little bit slower. So it had tried my initial increments of 10%, didn't work. Then it tried, oh, it's actually going pretty quick now. Then it tried 2.5%, that was successful, but on the next attempt of 2.5, it wasn't successful. So as we can see, we're slowly going through. This step time at the end here, this is the successful step time, and this is our total step time. So right now, we're at 17.5%. We just watch it kind of keep going on and on. So now we're at 21%. It's kind of keeping a consistent step time to increase the speed of those iterations. And yeah, this is the fun part, just watching ABAQUS go through all of the results. So my question for you guys, as we can see, little trivia, these two columns are exactly the same. Will they always be exactly the same? Or what's the difference between these two columns? Do you guys know? Total time and step time. Want to do some small chat while we're waiting for ABAQUS? Let's put it this way. What is going to be our total time? What is our total time for this analysis? Yeah, so that's yes and no. So let's start off with this. What is my total time for this analysis? I got a direct message saying 1, 1. It's not 1, it's 2. Because each step was a time period of 1. So my applied load is 1, and then my remove load is also 1. So what's going to happen is this total time tracks the entire analysis. So right from 0 all the way through apply load and all the way through remove load. This step time right here is just focused on the current step. So as we're going to see, once this step ends, as it's going to really quick, the applied load step, this will still keep going from like 1.2, but this one will just still be 0.2. So look, our first step is now completed, which was applying the load, and now it removes the load. So keep in mind that this carries on from the 1. This does not carry on from the 1. So this is like watching the second step from the start, and this is watching the second step from basically the start of the entire analysis. So hopefully that makes sense to you guys. So Bryce was right where it would change if we do change the pseudo time, but that's the main difference between the two columns. So now that our analysis is complete, we can right click it, go results, and if I were to show the deformed shape, it's going to go something like this. Something like this. So the thing that's interesting now is this right here is the final analysis file given. So this right here is without no load. So even without the load, it still has a deformed shape. The reason why is because we have that plasticity. We have those permanent strains. If I were to go up here, instead of going stress, I were to go to this PEEQ, which basically means the equivalent plastic strain. For those of you who did solid mechanics, you guys know exactly what this equivalent plastic strain is. If I were to click it, as we can see, this whole thing right here is very heavily strained. What I'm going to do is I'm going to go frame selector over here. And what we're going to do is we are going to go into basically look at a frame by frame analysis. So as we're going to go, we can see it keeps going, it keeps going. And as we can see, this step time right here, so we're at 78% of our applied load. It keeps going down. And what I'm going to do is I'm just going to go a little bit more slowly now. So we're at 0.99, and now we're at 1. So this is after we applied the load completely. Now in the next step, we're starting to remove the load. So if we go next again, as we can see, with the load coming off, it starts to go back towards its original shape. But even after the load is completely off, there's still so much strain in their permanent strains that it stays deformed. So how is that? How is that analysis? Was that fun? You guys have fun? Probably not at all. All right. So that's my introduction into constraints. The next ABAQUS example that we're going to be doing after we do the theory for a little bit is going to be on contact. So Mahmoud's asking, where is the vibrations? That's a good question. Where is the vibrations? Let me ask you a different question. If we're doing a static analysis, do we have vibrations? What do you think? It's because we're doing static. If we were doing dynamic, then yes. Keep in mind that all we're doing with this beam is we're just basically displacing it as a guess, and we're just making sure that equilibrium is maintained. No dynamic effects are actually maintained. If we were to change our steps, so we're going to model here, and in our steps, we were to switch from static over to dynamic, then things play a big difference. Because in dynamic, we don't have a pseudo time anymore. We have a real time. So what we do in a dynamic is we go to this amplitudes right here, double click it, and I don't know where it pops up. It's somewhere crazy. Yeah, I can't find where it popped up on the screen, but amplitudes. This is where we actually define how fast we load something and how fast we unload something. So this gets to be a lot of fun in a dynamic analysis. And if that was the case, then yeah, you would see it kind of come back to rest. Lots of fun. Great question, though. So is there any questions concerning this at all before we take a little bit of a break and get into our last one, which is going to be contact? You guys pretty confident? Can we have animation? Like, do you mean like a video? Yes, we can do a video. So if we were to go into visualizations, we can create a video where we basically do this. It's somewhere in, I forget where it is. It's, yeah, like movie, create, and you can actually create it. So you definitely can do that. That's definitely an option. Now, one of the problems though is this. If I were to go back, monitor. The problem right now is ABAQUS, every time it's successful, it stores one of these increments every time. So the problem is it becomes kind of inconsistent. So my time frame, I was able to jump 2.5% in this time. Over here, I was only able to jump 1.7. So what we can actually do is we can modify ABAQUS to only record very specific time increments. And I'm going to show you guys that in the next example. And that'll make our lives a little bit easier if we're trying to do a video. Otherwise, the video is based on the time step. So what happens is if there's an area where the time step is very small, a lot of the video will be basically nothing. And then it'll just zoom past the rest of the deformation. It's kind of crazy. But yeah. If there's no other questions, we're going to take a little bit of a break. We'll come back at 10:05, and we're going to cover the contact theory as well as do the next contact ABAQUS example. So if you guys have any questions, again, just throw it in the chat. I'll answer it after I come back. I will see you guys at 10:05. All right, guys, I'm back. I hope you guys had a nice break. Let's get into contact. Now, I know that, again, this is probably the most requested thing. This is what everyone gets really excited for when they start thinking about finite elements. So let's jump in. And Sabrina, I see your tip. Thank you so much. That's a great suggestion. I love it when you guys help me out like this. Makes my life a lot easier. All right, so let's jump in. So, got to turn on the clicker. Actually, no, I got to click the PowerPoint. Contact. So it's finally time to cover contact. You guys have been so excited. You guys waited so patiently. Too bad it was at the end of the course. Now, contact between two surfaces, it's actually quite complex because it's dependent on many mechanical properties. And if you're interested in thermal, it also depends on thermal properties. Now, I'm not going to lie, I'm not the expert on thermal, so I'm not going to speak on it too much. But when it comes to mechanical properties, there's a lot. So one of them, as you guys may guess, friction. Two surfaces intersect each other and rubbing against each other is going to be friction. Second one is normal behavior. Now, normal behavior in ABAQUS is simply this. If I have two surfaces that are coming together, I need to tell ABAQUS that when they hit each other, they hit each other. They create forces on each other. If you don't define contact in ABAQUS, you guys can still have two parts come together. The only difference is that they're just going to go right through each other. They're not actually going to stop and make those forces. So we have friction and normal behavior. But we also have other types. An example would be cohesive behavior. So let's say that I have my two surfaces, but I glue them together. Of course, there's going to be a cohesive bond. So even when I try to separate the two surfaces, they're actually going to stick together. So we can define that cohesive behavior between them. And we have failure. So after we glue those surfaces together, and if I were to start pulling, they're going to show that cohesive behavior. But we know that if I have enough force, at some point they're going to start to separate again. Now, what we can also do with that failure is specify the evolution of the failure. Is it a very sudden separation apart, or is it a very slow, almost prying separation? We can specify all that using contact. And this is actually defined in ABAQUS as an interaction property. So if you guys remember those tabs from ABAQUS, we had constraints, but we also had interaction properties and interaction. It works very, very similar to the material behavior, where in the material behavior, we define the material behavior and then we applied it to our part. Well, we're going to do the same here where we define the contact behavior and then we apply it to two surfaces. So when you guys click interaction property in ABAQUS, you guys get the following menu. Now, I already selected tangential, normal, damage, cohesive, so normally those won't be there. But what we basically do is we click down this mechanical list and we can start adding them. Again, this menu right here is very similar to the material properties command, where we basically go down and we select what we want. Now, when this interaction property is defined, we can actually apply it to our two surfaces, our master and our slave surface, as an interaction. So again, we create this property using the interaction properties command, and then we apply this property to our model using an interaction. And we're going to talk about what it means to have a master and a slave surface. We kind of already touched upon it in the constraint section, but when we talk about contact, it actually becomes very important, and this is going to be the reason why. So when we define contact, again, we're defining two surfaces, and we have to define one as a master surface and one as a slave surface. And all we really set up until this point is that our master surface is selected as the stiffer of the two surfaces. That's it. Now, the important definition that we're going to have here when we're dealing with contact is that the nodes of the slave surface slide on the master surface. All right, so this is the whole goal here. And this is why it's actually a special form of constraint. Remember, in our constraint example, we took a node and we said, all right, this node has a very specific movement path. Well, that's all we're doing when it comes to contact. We have our master surface and we're taking the nodes of the slaves and we're saying that it is now constrained to move along that surface. That's all we're doing. It's a special form of constraint. Now, again, as we said, the master surface should be the more rigid of the two surfaces, and this comes down to how it applies pressures, and we're not going to get into that. But another very important aspect is this. The slave surface should be of equal or denser mesh size compared to the master. This is going to be the big one right here. Our slave surface should have a more fine or smaller mesh size compared to the master. And here's the reason why. Let's say that I had a master surface and I had my slave surface. And what I'm going to do is I'm going to take my slave surface and I'm going to pull it down so that it makes contact. What's going to happen is this. Remember that all of those nodes on the slave surface, they are now constrained by that master surface. So once the slave nodes make contact with the master, that's when contact occurs. So in this case, it's actually good to go because we can see that our slave surface has a smaller mesh size than our master surface. What happens if we go to this scenario over here where, as we can see, our slave nodes, it's much more coarse. There's fewer slave nodes than master nodes. If I were to start bringing this down, what happens is the contact doesn't occur until those nodes hit the master surface. Well, this is a problem because if I were to bring this down, those nodes don't hit the surface until that point over there. And at this current point, we can see that half of that master surface is inside of the slave surface. So this is why we need our slave surface to be a smaller mesh size to make sure that we don't have any of that penetration. So if our slave surface is not properly meshed, we will have that penetration. So this is why we have the smaller size. Hopefully that makes sense to you guys. Now, one thing we're going to talk about is the normal behavior. So once we have our slave and our master surface specified, the first thing that we're always going to want to throw into ABAQUS is going to be the normal behavior. Now, what we can do with this normal behavior is we can define it as one of two types: hard contact or soft contact. What's really nice about ABAQUS is, again, these calculations are really complex, but ABAQUS makes it really nice and user-friendly, so you don't really have to do too much. All you really have to do in ABAQUS is specify hard or soft contact, and we're going to talk about what those two are. So let's say that I have a master surface and a slave surface, and I have this graph here. This graph right here is gap and overclosure. So this right here, the distance between these two surfaces right now, that's going to be our gap. Of course, as our gap gets smaller to the point where the surfaces are touching, well, then we're going to start applying a pressure. It makes sense. There's no pressure, but once they start touching and they start pushing on each other, the pressure between them is going to go up. Now this overclosure means that this surface actually starts penetrating into the master surface. So in the first case, if we were to look at our scenario right now, there is a gap between our master and our slave surface. So if we were to look at the graph, we'd be at, let's say, this point over here. As we can see, there's no pressure. And this makes sense because if they're not touching, they shouldn't be reacting off of each other. Now let's say I take that slave surface and I move it towards the master surface so that they're just touching, but I'm not actually pushing them together. They're just touching. Well, as we can see, our point has now moved to this point right here. Our gap is now 0, but we're not actually pushing on each other yet. Now if I were to take that slave surface and I were to push it into the master surface, what's going to happen is we're going to start creating reaction forces on those slave nodes. So what's going to happen is the gap is still going to be 0, and we're going to go up in pressure. And this right here, this is called hard contact. And this hard contact is what we'd expect in reality. If I were to take a pen, I were to take a piece of paper, and I were to go, I still have a gap, no pressure. I'm just touching, no pressure. But if I were to go further, I start to have that pressure and it pushes it. Again, this is called hard contact. But in ABAQUS, we have something else called soft contact. And what this is it takes this curve and it actually modifies it to look something like this. Now, it won't always be exponential. You guys can actually define it as kind of a table yourself if you want. But one of the default options is this exponential. Now, what does this mean? Well, this means a couple of things. One is, if we can look, we can see that there is a point in which we still have a gap, but the pressure is non-zero. That means that once the slave surface becomes close to the master surface, it starts to apply the pressure, even though it's not touching yet. And if we were to look over at the next point over here, we can see that there is a point where there's pressure, but we have overclosure, which means that our slave surface is actually inside of the master surface. Now this right here, in reality, this isn't realistic. We don't just have things going inside. Oh, I probably shouldn't do that on camera. But we don't just have things going inside of each other. However, we do this because it helps us computationally. If we were to have a model with a lot of contact, and we have a lot of pieces suddenly going from 0 force all the way to a lot of force, it creates a lot of nonlinearity. So soft contact, which is this behavior right here, we typically do this if we have a lot of convergence issues. So hard contact does not allow any overclosure, which is accurate to real life, but it can lead to some numerical instabilities. Soft contact allows some overclosure, and if we were to look at the graph here, I kind of really did a lot of overclosure, but realistically it's very tiny amount of overclosure, which helps reduce, or I guess this reduces the accuracy, but it helps with those numerical instabilities. Now, personally, if I were to use hard contact and find numerical instabilities, there's a bunch of different ways you can kind of help mitigate those instabilities while still keeping the hard contact. But that gets a little bit complex. It's kind of outside the scope of this course, so we're not going to talk about that too much. The second one is the tangential behavior, which is basically the friction behavior. Now in ABAQUS, we have a lot of different ways to define what we want for the tangential behavior. If we want to, we can say it's frictionless. They can slide on each other and no friction forces are created whatsoever. However, if we want friction, we basically have two different methods we can use. We can define the friction using the penalty method, which we discussed, and we can define the friction using the Lagrange multiplier method. Another thing we can do if we really want some fun is we can define a rough surface, which means that once they come into contact, there's no more sliding. They're kind of stuck together in that way. Now, the most popular method is the friction using penalty method. This allows us to create the friction in the model by only specifying a friction coefficient. If I were to show you guys a picture right here, as we can see under tangential behavior, the only input that we have is our friction coefficient. So if you guys know the friction coefficient, you just throw it in there, you guys are good to go. Now, we can also define the maximum shear stress and the maximum elastic slip if we want. As we can see, there's kind of tabs over here to do that. So if you guys want a more complex analysis, there are ways to do that. However, most of you guys, friction coefficient, that's usually good enough. So that is contact in ABAQUS. As you guys can see, that's the end of the PowerPoint, because it's one of those things that I can only explain it so much. The best way to show you guys is through actually doing an example. So what I'm going to do is I'm going to start up ABAQUS yet again, and we are going to go to our second example of the day. If I can find out where I put it. I think I exited out of it. All right, so give me 2 seconds, guys, while I pull it up. Contact in ABAQUS. We're going to do this example right here. Hold on, I'm just going to bring ABAQUS to the other side. Zoom chats are always so much fun to move around. All right, so ABAQUS is up, and my example is up. So this is going to be the example that we are going to do. It's a very simple example where we basically have a beam or a plate, and we are going to push on that beam with this rigid cylinder. All right, so we're going to push down using this rigid cylinder. So it wants us to displace this indenter, this rigid cylinder, downwards by 50 millimeters. And then after that, we are going to pull it back up by 50 millimeters. It says that the Young's modulus and the Poisson's ratio of the plate are 200,000 MPa and 0.3. The plate yields at 345 MPa and has an ultimate strength of 400 MPa and an ultimate strain of 20%. Use plane strain and symmetry. So that's one thing that we have to discuss. And it says that the frictional coefficient between the indenter and the plate is 0.3. So if I were to employ symmetry, I'm going to ask you guys kind of conceptually here. Is my line of symmetry going to be vertical, or is it going to be horizontal? What do you guys think? Is my line of symmetry going to be horizontal or vertical? I got a private message saying vertical. Completely correct. So what we're actually going to do is only model this half of the beam over here. Now, when we're using symmetry, it's usually great, but there's something you have to be aware of, and we're going to talk about that after it kind of happens. So what we're going to do is we're going to model this. We know that the complete distance is 200, but again, I'm only going to model half. So the first thing I'm going to do is I'm going to create kind of this half of the plate. So I'm going to go to parts. I'm going to say, you know what? I'm going to create my plate right here, and it's 2D. So I'm going to switch back to 2D, and our plate is actually deformable. So I'm going to say, can we take both? And the answer is no. So one of the things that we have to do about symmetry, or things that we have to consider when we're dealing with symmetry, is the loading. Not only does the geometry have to be similar or symmetric, the loading does too. If I were to take a horizontal slice and look at the top, well, the top has this load due to the cylinder. The bottom does not. So it's actually not symmetric horizontally. Does that make sense? Hopefully. I'm not sure what you mean for each part. When we're talking about symmetry, we usually don't do it for parts. We do it as kind of a whole for the model. Okay. All right. So yeah, if you have questions, just let me know. So we're going to go back. 2D shell. We're going to go continue. And again, normally our plate is 200 by, what was the thickness? 200 by 25, but we're only modeling half. So we're going to go 100 by 25. So I'm going to start at 0, 0. And I'm going to go 100, 25. So if I were to zoom out, we can see that we have half of our plate. I go done. We have half of our plate. Now, this is going to be the key to your guys' assignment, and when we're dealing with a lot of these contact problems. This cylinder right here is rigid, a rigid cylinder. So what we're actually going to do is we are going to define this surface right here. We're going to define kind of this curve right here. So what we're going to do is we're going to create a second part for this indenter. Part, we're going to go indenter. But instead of deformable right here, we are going to go to analytical rigid. Analytical rigid. Now, analytical rigid is when we just define things like surfaces. Something simple. Discrete rigid up here, which I know a lot of you guys will probably want to try and click. This is when we actually want to create rigid elements. Rigid elements. That's a whole different game that creates a lot of complexities in the contact formulation. We're not dealing with that. So we're going to go analytical rigid. So what if both were rigid? So my question to you is, if I have two things that are rigid, what am I trying to achieve? So that's my question. So you could have them both as rigid, but you're not really achieving anything. if that makes sense. So if I wanted this as rigid, like I'm not sure if you mean defining the part or if you mean like loading, or I'm not familiar. What is CLT? Actually, you know what? We're running short on time. Send me an email and we can discuss. We got little under half an hour to finish this example. Okay, yeah, perfect. And if it's something that I think the class should know, I'll send it to the class too, so you guys won't be missing out. So we'll go analytical rigid, continue, and again, we're just defining the surface. So we actually don't need to model the entire cylinder, because if it's rigid, there's no deformation inside of the cylinder. So there's not any stresses, there's not any strains. So this is why we're actually just going to define the surface of the cylinder, because that's what's going to come down and make contact with the plate. Now, I don't really know why. I'm going to be honest with this. When we define surfaces as an arc in ABAQUS, these analytical surfaces, they have to be less than 180 degrees. So I can't actually draw half a circle. It has to be a little bit smaller than half a circle. I'm not entirely sure why. But yeah. So what we're going to do is we're going to create an arc using this command right here, create arc. And it says pick the center point for the arc. And I'm going to have it right over here. Now, normally what I would do is I would say, all right, well, the radius is 25. So I'm going to start over here, and then I'm going to go all the way around over to this side. But again, we can't have 180 degrees. I'm not entirely sure why. So what I'm going to do is I'm going to start just a little bit below. So I'm going to go basically negative 24.5, comma, negative 5. So I'm just keeping the same thing, except I'm starting a little bit lower. And I'm going to go over. Oh, I don't know what I did there. Hold on. Go back to the arc here. Negative 24.5, comma, negative 5. Start point for the arc over here. And we're going to come down over to here. So as we can see, I didn't actually draw this little last part needed for the complete half circle. Again, I don't know why half circles don't work 100%. But this is going to be our rigid indenter. Again, it's just the surface. So I'm going to go done, good to go. And now we have our rigid indenter. So now we have a plate and we have our indenter. So that first part's good to go. Part's now defined. We can go over to property. So if I were to go to property, I can start inputting my stress strain behavior. So this is going to be for our plate, and our plate is very reminiscent of steel. So I'm just going to call it steel. I'm going to go mechanical, elasticity, and elastic. So for our Young's modulus, 200,000, given in the question. And our Poisson's ratio was 0.3. So I'm just going to go back, make sure that those are correct. 200,000, 0.3. We're happy. So our elastic properties, good to go. If we were to go to plasticity and go to plastic, it says it yields at 345 MPa, and we know our plastic strain at yield is going to be 0. But I'm going to go back to the question, what's going to be the next value of stress that I input? What's my next point going to be? I already have the 345 and 0. It says the ultimate strength is 400 at an ultimate strain of 20%. So what is going to be my stress point that I input? I got a private message saying plastic strain, but what I'm asking for is what value of stress do I input next? This says 400. Well, I'll start with simpler questions. Do I input 400? Who thinks I input 400? The answer is no. This is our engineering stress and our engineering strain. So right here, this 400. Do I input 400 if it's still engineering stress? This is what will get you guys. We need the true stress and the true strain. So what is 400 MPa in this point in terms of true stress? What do you guys think? What is this 400 MPa in terms of true stress? 400 times 1.2? Exactly. It's 480. So as we can see, once we get into the large strains, so at 20%, this starts to increase quite a bit. So this right here, this next point, it would actually be 480. For the plastic strain, what we would do then is we'd find the the true strain, and then find the plastic strain. It works out to be around 0.18. So just kind of the thing I want to show you guys is be really careful about the engineering stress and the true stress, stuff like that. That's what will get you, and this will make quite a big difference in the results later on. But we're not really focused on material behavior in this example. We're more concerned about contact. So our material behavior is good to go. I want to start assigning it, so I'm going to switch back to my plate. I'm going to create a section, and we'll just call this steel. Why not? Or steel section. Make it even more fun. It's homogeneous. We click continue. Our material is steel. Good to go. And then I simply apply it to our shape. It's green. It means that we're good to go. So what we're going to do is we're going to say, all right, good. We can go to property, or sorry, assembly now. And we are going to bring in our plate. Okay. And then we will also want, so we're going to apply it. And then we're also going to bring in our indenter. Oops. Good to go. So what I'm going to do is I'm going to move this indenter just above. Just above right here. So I'm going to go translate instance just like we would before. I'm going to click our indenter surface, go done, and then I'm going to pick this center point right here, and I'm going to move it just above our plate right here. So right now our plate is 25 millimeters high. I'm going to put this at, let's say, 26 millimeters. So the gap right now is only 1 millimeter. I'm going to say, is this okay? Yes, this is okay. So this is all I'm doing in the assembly tab. I'm just rearranging things so that they look very similar to what's actually going on over here. So after the assembly tab, we have our step tab. And in our step tab, we have two steps, just like the previous example. We have apply load and we have remove load. So I'm going to create a step. We're going to call this simply apply load, continue. We're going to turn on nonlinear geometry. And we are just going to decrease these step sizes a little bit just to make sure we have a nice smooth analysis. To 10, good to go. And I'm going to create my second step, which is remove the load. I don't need the, I guess. That sounds a little silly. Just remove load, continue. Nonlinear geometry is on by default. We're going to switch these bad boys to 0.1, 1,000 increments, even though, of course, we don't need 1,000 increments. And we go, okay, so now our steps are good to go. If I were to go here, we're good to go. Now I'm going to show you guys something kind of fun. And you guys think, Clayton, this isn't really fun. You're being an idiot. But if we would go down here to these requests right here, and we were to click them, and they appeared behind Zoom chat. So what I did is I just clicked this field output request. We can actually do some very nice things here. What this basically does is this tells ABAQUS what to output in the model. So if I want to, and I want to make my analysis smaller, I can say, you know what, ABAQUS, I don't need the stresses. Don't show me the stresses. Don't calculate them. That's what you do in this command right here. Of course, we want our stresses, so I'm going to keep it on. But this is what I'm going to play with right here. This frequency right here, we're going to go to X unit of time. So remember, right now, ABAQUS, every successful increment, no matter how small it is, it records it. And what happens is when you have a model with a lot of increments, let's say 1,000 increments, ABAQUS is storing all that information 1,000 times. That's a lot. And what usually happens is the distance or the difference between two increments is small. You don't need it to store all that. And what happens is your model files become really large. Some of my ABAQUS files, when I didn't use this, they become like 36 gigabytes because it's storing so much information. What we can do is we can tell ABAQUS, hey, I don't need all of the information. Only store the information at, let's say, a time step is 0.1. That's it. So what'll happen is even though let's say I need 1,000 increments, ABAQUS is only going to store 0.1, 0.2, 0.3, etc. So if you guys are worried about memory size, stuff like that, this is the way to go. We switch this to every unit of time instead of every increment, and then we can specify the fraction of our timestamp. So basically at every 10%, ABAQUS will actually only store those results. And this will make more sense a little bit later. So that's our step. Then we're going to go down into our interaction. Now our interaction again is going to be nice and fun. We have to define one constraint and one contact property. So which one do you guys want to do first? The constraint or the contact? The constraint or the contact? Completely up to you guys. No one cares at all. Contact, I got a private message saying contact, we will do contact first. So before we're playing around in this create constraint menu, create constraint. But now we're going to go be playing around up here with these two buttons. So this button right here says create interaction property, and this one right here is just create interaction. So again, this button right here, this is where we define the behavior of the contact. And then we apply that behavior using this button right here. So we're going to go down here, create interaction property, and it says, what kind of interaction do you want? Well, I'm going to call this contact, and the interaction that I want is simply contact. So I'm going to click contact, and then you guys get this menu right here. Again, it looks very similar to the material properties menu. From here, we can select all the different types of contact we want. So we're going to go say mechanical. We have a friction coefficient. So we want to define some sort of tangential behavior. Again, the most common one for a friction coefficient is penalty. So instead of frictionless, I just come down to penalty, and I just input my friction coefficient, which was given as 0.3. That's it. I also have to define the normal behavior. So I'm going to click normal behavior, and by default, it's at hard contact, and it allows the separation after contact. So if we want to, we can disable separation after contact, which means that after the indenter makes contact with our plate, and I were to pull the indenter up, it's going to bring the plate back up too. Of course, we don't want that in this model, so we're going to allow that separation after contact. So after I push down on that plate and I lift the indenter back up, the plate is still going to stay deformed. And that's all I'm going to define for this example. As you guys can see, defining contact is actually really simple. I throw in my friction coefficient, I specify hard contact, I'm good to go. So I can go OK. So if I look at my interaction properties, I now have contact defined. So now what I'm going to do is I'm going to take this property that I defined and I'm going to apply it to my model here. I do that using interaction. So I can either go create interaction or I can double click interactions over here. So as we can see, there's a bunch of different ones. What we are going to do is we are going to have our surface to surface contact. And we'll just call this interaction contact. So surface to surface contact, I'm taking the surface of that indenter and I'm putting it down onto the surface of the plate. Makes sense, right? So I'm going to go continue, and it says select the master surface right down here. Select the master surface. So question for you guys, which one's the master surface, the plate or the indenter? The plate or the indenter? What do you guys think? Which one is going to be my master surface? So you guys think it's the plate right here? I got a private message saying indenter, so it's 1-1. Oh, and I got another indenter. It is the indenter. It is indeed the indenter because, again, the master surface should be the more rigid. Since this is perfectly rigid, we know that it's going to be more rigid than the plate. So I'm going to select this surface as my master surface. So I'm going to go done, and it's going to say which side is going to make contact. So this is one of the things that you have to deal with when you deal with just wires. So which side, what do you guys think? Is it going to be the yellow side that makes contact, or is it going to be the magenta side that makes contact? What do you guys think? Yellow, exactly, because this side of the indenter is going to be making the contact. So we're going to click yellow. Then it's going to say choose the slave surface. Now we have two different things we can do. We can go surface or node region. So we're just going to go surface, make our lives easier. And then it says select the slave surface. Well, we know that this indenter is going to make contact with the top surface of our plate here. So I selected that, I go done, and then this menu appears. And you don't actually have to do too much in this menu if you're doing a simple analysis. You just make sure that your master surface is picked, your slave surface is picked, and that your interaction property down here is the one that you defined. So if you have many different interaction properties, this is where you can pick which one you want to apply. We only have the single one, so by default it goes to the one we defined, but we can go OK. So now remember when we did a constraint, it had yellow circles. For contact, it has these yellow squares. So as we can see, the yellow squares over here and the yellow squares over here, it means that there's now contact defined between those two surfaces. So that's going to be the contact. That's good to go now. Now I said that there's going to be a constraint. All right, I said there's going to be a constraint. What is going to be my constraint? What am I talking about? What do you guys think? What do you guys think my constraint is in this problem? It's definitely a hard one to guess. All right, we're on time constraints, so I'll tell you. When we're dealing with a rigid body in ABAQUS, just like in the previous example. Oh yeah, no, I got a private message. Yeah, you're completely correct, Mahmood. When we're dealing with a rigid body, we can't apply a displacement directly to the rigid body. We control the rigid body through a reference point. So our constraint is going to be creating a reference point to basically control this indenter. So you're correct. I had a private message that said the movement of the indenter. That's completely correct. So the first thing that we need to do is we need to create a reference point for this indenter. So I'm going to click reference point, and I'll just select up here my reference point right here. And then now we need to create a constraint that basically says that this surface right here, this rigid surface, is controlled by this reference point. So I'm going to go to create constraint over here, and I'm going to say indenter. Let's call it indenter. And we know that we are doing the rigid body constraint. So I'm going to go continue. And again, we just have to select our two things. So our reference point, that's nice and easy. We only have the one, so I'm going to click it. It now says picked. And then over the region, we are selecting our analytical surface. We're not selecting a bunch of nodes anymore. We're actually selecting that analytical surface. So I'm going to click that. It says select the surface. Well, that's going to be our indenter yet again. So I'm going to click OK. And it's going to say, well, which side of the indenter? We already discussed that it is going to be the yellow side. So now we have our surface defined. We have our reference point defined. We are good to go. So now we can see that there's kind of those little circles inside of the squares, meaning that there's also a constraint on this indenter. So far, so good. We are now done with our interactions. We can move on to our loads. So really quick, any questions? Are you guys feeling confident, or is there something confusing? How are you guys feeling? All right, I'll take it as you guys are good. Again, any questions, just let me know. Happy to answer what you guys have. Perfect. So we got load, and we have to apply two boundary conditions, basically. Two boundary conditions and one load. So what we're going to do is we're going to start off with the easy boundary condition. So I'm going to create a boundary condition, and we know that we have a fixed end. We know right from the problem that this end is going to be fixed. If I were to model this half of the beam, then this end would be fixed. But we modeled this side, so we need to fix this end. So that'll be in our initial step. It'll be displacement. We simply select it right here, go done, and we are basically restraining any displacement at that end. So that should be nice and easy. Now, since we did a vertical line of symmetry, we also have to apply symmetry to this side over here. So I'm going to go down to my boundary conditions. I'm going to add a second one, which is going to be symmetry. Go up to symmetry, continue. I'm going to select this surface right here, go continue, and then it's going to say, well, what kind of symmetry do we have? Now that's going to be my question for you guys. We know it's not going to be any of these. I'll just keep it nice and simple. Is it going to be X symmetry, or is it going to be Y symmetry? What do you guys think? X or Y? Two guys saying X. I'm getting a barrage of X. You guys are completely correct. A nice way to check is just look at U1. This point, this line here that I have, when I push down on the indenter, it's not moving side to side. It's simply just going straight down. So we know that U1 here is always going to be equal to 0. So it is going to be X symmetry. You guys are so smart. We are good to go. So in terms of our actual plate, we're good to go. But now we need to specify the movement of this indenter. So what we're going to do is we're going to create another displacement, and we're going to put this in our applied load step. So this is going to be, I'll just say apply load. So we are applying this indenter down into our plate. So this is going to be a displacement. So we're going to go down to displacement. We're going to go continue, and it says select where you want to apply it. Well, we're going to apply it to the reference point. Remember that the reference point is basically this surface. If I were to move the reference point down, I'm moving that whole surface downwards. So I'm going to click OK. And we know that we want to displace it by a distance of, let's say, 50 millimeters straight downwards. I believe that was given in the question, 50 millimeters. Yeah, 50 millimeters downwards. So what we're also going to do to make sure that everything is stable is we're going to just specify that this indenter is not going to move horizontally. It's not going to rotate. It's simply just going to come straight down by a magnitude of 50 millimeters. I'm going to go OK. And as we can see, we now have this downward motion. We're good to go. But again, this was just the apply load step. In our next step, we want to take that indenter and we just want to pull it back up. So we apply that load through the indenter and then we pull the indenter back up to remove the load. So I'm going to create another displacement and we're going to call this one remove load. So what we're going to do is we're going to put this into our remove load step. We're going to keep it as a displacement and we're going to go back to our reference point because again, that's what controls the indenter. And we are going to have a displacement back upwards of 50 millimeters. And again, to keep things stable so that there's no wobble, anything like that, we're going to keep the rest as 0. Now, as you guys can see, and this is what I was kind of hinting to last example, is the loads from the previous step are always propagated into the next step. So currently in this remove load step at our indenter here, we're applying a displacement in both directions. This will cause things to diverge very fast. So what we actually have to do is in our boundary conditions, we're going to right click and go manager. And we are just going to see what happens. So I'm just going to extend these out so that we can see apply load and remove load. So our fixed end and our symmetry were created in the initial step and they're kept all the way through and that's exactly what we want. We apply our load in our applied load step, which is good, and we remove the load in our remove load step. The thing that we actually have to change is this right here. Because by default, this load of 50 millimeters downwards, that's going to keep active in our next step. We don't want it active. We want to actually take it apart. So we're actually going to deactivate it. So in this step right here, we are removing that load. We just simply get rid of it. So if I were to go back here, we can see that in this step, remove load, we now only have a displacement upwards. And this is very easy to see. So if I were to go to my applied load step, we can see that this moves downwards. If I were to go to my remove load step, this simply goes upwards. Makes sense to you guys, hopefully? Nothing too crazy yet. Perfect. All right, so that's going to be our loads. Last thing that we have to do is our mesh. So we're going to go to our part. We have our plate. And were we given plane stress or plane strain? Plane strain. So now we're going to go, all right, well, the first thing I'm going to do is pick what type of elements. Let's go plane strain over here, linear, and should we keep it reduced integration? It won't matter too much. Yeah, let's keep it reduced integration. Save us some computation time. If you guys want to play around with it later, by all means, go ahead. So this, we're going to apply, let's do a very thin mesh. So let's go 2, let's go 1. Oh, it's 25 tall. Let's go 2.5. Mesh like this. Good to go. Do we mesh the indenter? What do you guys think? Do we mesh this indenter? No, it's rigid. Remember, the purpose of a mesh is to figure out stresses and strains. We find those displacements of the nodes, stresses and strains. This is analytical. There are no stresses or strains. It's completely rigid. So we actually don't need to apply a mesh to our indenter. So after we're done the mesh, we can go down and create our job. We're going to call this, let's call it contact test. Contact test, we'll go continue. It's 2D, so I probably don't need to give it any more juice. And we are going to submit it. So I probably forgot something, but let's see what happens, shall we? So what I'm going to do, we're going to monitor it together. Just kind of see what happens. Submitted, started, running. If you guys can have a model that's running, that's usually, it's a good sign. If you mess up something like you forget a mesh, this will never even run. So that's kind of a hint at what you do. All right, so it's going. We're at 61%. Oh, we're at 1%. So that actually went pretty fast, as you guys can tell. Oh, and then we're in our second step where we remove the load. All right, we are good to go. So now we're going to go results. And as we can see, this is our deformation. So that happened. This is the last time step, so we're going to go back to the first time step. So as we can see, the indenter is slowly displaced downwards. It starts creating those stresses in our beam. It goes all the way down. Remember, this is our time step, so it's at 62%. So if we were to keep moving forward, we're at 70, 80%, 90%, and now we are at 100%. So after that, we said after this step, we're going to just start moving this back upwards. So as we can see, it starts to come up, and that's it. Nice and simple. So if I wanted to measure the force required to displace it 50 millimeters. Remember, I know that it displaced 50 millimeters, but I don't know the force it took to actually displace it 50 millimeters. What I can do is I can go to my XY plot, just like you guys did before, field output. What we are going to do is we are going to monitor that reaction force on the node, because that force required to push down, it must be the same as the reaction force on the node. So what we're going to do is we are going to go unique nodal, measuring something at the node, and we are going to measure the reaction force in the vertical direction. So I'm going to go RF2, and then in my elements nodes, I'm going to go to node sets, and I'm going to measure it on my reference point. So I'm going to plot it just like this. So as we can see in our time step here, we have kind of our elastic branch, and then it goes up something like this. And at this point right here, we are done displacing it downwards, and then we start going back upwards with the indenter. So of course, as the indenter goes back up, our load goes to 0 and it stays at 0. So if I wanted to figure out the force at the indenter at the very end to displace it 50 millimeters, it would be negative 4.5 times 10 to the 3 newtons. Or is it? My question for you guys, is my peak load around negative 4.5 times 10 to the 3 newtons? What do you guys think? Is my peak load this peak load right here? The answer is no. Does anybody know why? It's a very simple fix. We're not far off. But does anyone know why it is not 4.5? Does anyone have a guess at what it would be? It's a hard question to answer. This is one of the things that we always have to keep in mind. It's because we're using symmetry. When we're doing symmetry and we're looking at our reaction, we're only getting this reaction over here. But we know that there's another reaction over here. So since I did symmetry here, if I want the actual peak load for this entire thing, I need to times all my loads by 2. Because this would be the reaction over here, and then we have to multiply by 2 to count for the reaction on the other side. Does that make sense to you guys? Don't forget to do that in your assignment. Assignment says to use symmetry. So if you guys are using symmetry in one of these scenarios, you always have to times our load by 2. Just because we're only capturing basically 1/2. And yes, that's contact in ABAQUS. Is there any questions about this at all? You guys have any concerns? I have one last thing to tell you guys. Why did it look like this? Because this is a good question. So are you asking why this still looks like there's a surface in this part right here? Other side. I'm not sure, like over here? Under. I'm not too sure where exactly. Sorry, I'm not too sure where in the model. You mean right here? Because I don't see a surface. Opposite side. That's because it's just yielding so much. So one of the things, if we were to look at really quick, if we were to go into our, look at this strain right here. Our actual ultimate strain was 0.2. We're at 1 right now. So it's just one of those things that at this point right here, this is just straight up yielding. It's just being pulled. This is like almost like a cheap rubber right now, just nice and easy. Does that make sense? Why this is just yielding so much. If I were to go into our stresses, we can see that there's a high degree of stresses. All right. So the last thing I want to tell you guys is this. When we have contact problems, we have to make sure that our contact is applied very slowly. What happens is, and this is something that's completely outside the scope of the course, and this is something that there's a lot of research going into now, is contact algorithms to basically say, all right, I need to make sure that this surface knows where this surface is. They have to track each other to figure out when the contact is established. So if I were to take this cylinder, and instead of going like slowly and approaching the surface, if I were to just slap it, you're going to have a lot of divergence problems. So when we're dealing with these problems and we have an initial gap, we need to apply our cylinder really softly. Really softly. Does that make sense to you guys? We can't just slap it on. We have to go kind of nice and soft into the problem. I'm hoping that makes sense to you guys. We have to go nice and soft, otherwise it'll diverge really fast. So we have to go nice and soft into the problem. We can't go really fast. Now, if I were to take this exact same cylinder really quick, and I were to apply a load of 10 newtons on it, would my analysis converge? We're out of time, and I'm sorry for wasting your guys' time, so I'll just tell you. The answer is no. This won't converge, because if I have something floating in space, and I were to apply a force, even a small force, that displacement is technically infinite. So if I were to apply force control on this right now, what would happen is this just slam into the surface and it would diverge really fast. So if you guys have to use load control in this scenario right here, what I would recommend, or kind of the best way to do it, is you take our cylinder and we apply it a displacement of 1 millimeter just to get it into contact, and then you apply your forces. Like that, if that makes sense. Now, Bryce asked, is there a way to quantify that? Quantify what exactly? How slowly the contact should be? No, but usually it depends on the scenario. That's why it gets hard to answer. It's like mesh size, where it really depends on the scenario. Usually you'll be, it depends on the gap, it depends how much contact there is, so that's one of the things you can't really, it's more or less trial and error. So usually what'll happen is, let's say that you have this exact scenario and you don't know, try an increment of 0.1, so 10%, and if it diverges, say, you know what, maybe that was too fast, then try a smaller increment. And it's kind of more of a trial and error basis. This is actually really nice because it's only making contact kind of in the one spot here. And the contact is simple. It's just friction and normal contact. If I were to add cohesion here with damage, things get messy. Things get really messy. So it's very scenario dependent, yes. It's one of those trial and error things. If it diverges, just to try applying it slower, and typically it'll work. Yeah, no problem. All right, guys, so time's up. You guys can head out if you guys want. Last thing I just want to show you guys, though, really quick, it's just your assignment so that you guys can see what the contact problem is. We have a cylinder. We're going to apply a rigid indenter at the bottom, so just a horizontal surface. We're going to apply a circular rigid indenter at the top, and we're just going to pull that indenter downwards to crush basically this deformable cylinder. That's it. Sound good to you guys? Yes, exactly. We can relate the U1 and U2 displacement using the ellipse equation. That's why I kind of threw in part A rather than jumping into A and B, because we can relate them to using the constraint equation based on the ellipse. That's a great question, Eric. That's exactly what we do. Yes, and this constraint equation, we always make it equal to 0. Yeah. No problem. Yeah, and the reason why is because when we're dealing with that minimum potential energy, we know that if we take the derivative of the potential energy, it's equal to 0. Well, it's going to be the same thing here once we apply our constraint, equal to 0. Nice and easy. I'll stick around if you guys have any more questions, but if not, I want to apologize. I was 10 minutes late. ABAQUS examples usually take too long. But no, thank you guys for coming out. Second last lecture. Last week is the last theory lecture. Can't believe it. Time's gone by too fast. I've been having a lot of fun. I hope you guys have been too. All right. You guys have a wonderful day. Enjoy the sun. And now that daylight savings is, we can have a little bit more sunlight at night, which is nice.